Have you ever wondered what it would be like to witness the beginning of the universe? To see the first galaxies forming and uncover the secrets that created everything we know today? Let's explore together how the universe came to be, how it evolved, and how it continues to surprise us with each new discovery. Now take a deep breath, relax, and let this video guide you into a peaceful sleep as you learn fascinating facts about the cosmos. The formation of galaxies is a fundamental process that has shaped the visible universe we observe today. This cosmic phenomenon, occurring over billions of years, involves the intricate interplay of gravity, dark matter, and baryonic matter, resulting in the diverse array of galactic structures that populate the cosmos. Understanding galaxy formation is crucial to our comprehension of the universe's evolution and structure on the largest scales. The process of galaxy formation begins with the primordial fluctuations in the early universe, mere fractions of a second after the Big Bang. These tiny variations in density, believed to be quantum fluctuations magnified by cosmic inflation, set the stage for the gravitational collapse of vast clouds of primordial gas. As the universe expanded and cooled, these density perturbations grew under the influence of gravity, eventually leading to the formation of the first protogalaxies. The role of dark matter in this process cannot be overstated. Cosmological simulations and observational evidence strongly suggest that dark matter, which interacts only through gravity, formed the initial scaffolding upon which galaxies would eventually build. Dark matter halos, massive structures of this invisible substance, began to form first, creating gravitational wells that attracted normal baryonic matter. This process, known as hierarchical structure formation, is a cornerstone of our current understanding of galaxy evolution. As baryonic matter fell into these dark matter halos, it began to cool and condense, forming the first stars and protogalactic structures. This era, occurring roughly 100 to 500 million years after the Big Bang, marks the beginning of the epoch of rayonization, a pivotal period in cosmic history. The intense ultraviolet radiation from these first stars began to ionize the surrounding neutral hydrogen, gradually making the universe transparent to visible light. The formation of these early galactic structures was not a peaceful process. Mergers and collisions between protogalaxies were common, driving intense bursts of star formation and shaping the morphology of the emerging galaxies. These galactic mergers continue to play a crucial role in galaxy evolution to this day, with our own Milky Way bearing evidence of past merger events in its stellar halo and streams. As galaxies continued to evolve, they developed distinct structures and populations. Spiral galaxies, like our Milky Way, formed rotating disks of gas and stars, while elliptical galaxies took on more spheroidal shapes. The mechanisms behind these different morphologies are still an active area of research, with factors such as angular momentum, gas accretion rates, and merger histories all playing roles. Star formation within these evolving galaxies is a complex process governed by the interplay of gravity, turbulence, and magnetic fields. In the dense molecular clouds of galactic disks, pockets of gas collapse to form new stars, enriching the interstellar medium with heavy elements through stellar winds and supernovae. This cycle of star formation and feedback is crucial to understanding the chemical evolution of galaxies over cosmic time. Recent observations, particularly from space-based telescopes like Hubble and James Webb, have pushed our understanding of galaxy formation to ever earlier epochs. The discovery of galaxies at redshifts greater than 10, corresponding to times less than 500 million years after the Big Bang, has provided invaluable insights into the early stages of galactic evolution. These observations challenge our models and push the boundaries of our understanding of how quickly the first galaxies could form and evolve. The chemical evolution of galaxies is another key aspect of their formation and growth. As successive generations of stars form, live, and die, they gradually enrich the interstellar medium with heavier elements. This process, known as chemical enrichment, leads to an increase in metallicity over time. Observations of the chemical composition of stars and gas in galaxies at different redshifts allow astronomers to trace this enrichment history, providing a cosmic chemical timeline. One of the most challenging aspects of understanding galaxy formation is the role of feedback processes. Supernovae, stellar winds, and active galactic nuclei, AGN, can inject enormous amounts of energy into the interstellar and intergalactic medium, regulating star formation and even expelling gas from galaxies. These feedback mechanisms are crucial for explaining the observed properties of galaxies, such as the galaxy luminosity function and the relationship between galaxy mass and star formation rate. The study of galaxy formation has been revolutionized in recent decades by the advent of large-scale cosmological simulations. Projects like the Illustris and Eagle simulations use supercomputers to model the evolution of large volumes of the universe from shortly after the Big Bang to the present day. These simulations, which incorporate our best understanding of dark matter, gas dynamics, and stellar physics, have been remarkably successful in reproducing many observed properties of galaxies and large-scale structure. However, significant challenges remain. The Cuspy halo problem and the missing satellites problem are two examples where observations of galactic structure, particularly in dwarf galaxies, seem to conflict with predictions from simulations based on cold dark matter models. These discrepancies have led to ongoing debates about the nature of dark matter and the possible need for modifications to our cosmological models. Another frontier in galaxy formation research is understanding the role of the cosmic web. Recent observations and simulations suggest that the filamentary structure of the universe plays a crucial role in feeding gas to galaxies and shaping their evolution. The interplay between galaxies and this cosmic web, including processes like cold gas accretion along filaments, is an active area of research that promises to shed new light on galaxy formation and evolution. The study of galaxy formation also has profound implications for our understanding of the universe as a whole. The distribution and properties of galaxies serve as crucial probes of cosmology, allowing us to test theories of dark matter and dark energy. Moreover, understanding galaxy formation is essential for addressing questions about the prevalence of life in the universe, as it sets the stage for planetary formation and the potential for habitable environments. As we look to the future, new observatories and technologies promise to revolutionize our understanding of galaxy formation. The James Webb Space Telescope is already providing unprecedented views of the early universe, while upcoming facilities like the Vera C, Rubin Observatory and the Square Kilometre Array will survey the sky with unprecedented depth and resolution. These observations, combined with advances in computational modeling and theoretical understanding, will undoubtedly lead to new discoveries and insights into the complex process of galaxy formation. In conclusion, the formation of galaxies represents a grand cosmic narrative that spans billions of years and encompasses a wide range of physical processes. From the first primordial fluctuations to the rich diversity of galaxies we see today, this story is one of constant evolution and interaction. As we continue to push the boundaries of our observations and refine our theoretical models, we move closer to a comprehensive understanding of how the universe transformed from a nearly uniform sea of gas into the magnificent cosmic structures we observe today. As we delve deeper into the mysteries of galaxy formation, we naturally turn our attention to the enigmatic objects that often lie at their hearts: supermassive black holes. These cosmic behemoths, with masses millions or even billions of times that of our Sun, play a crucial role in shaping the evolution of their host galaxies and pose some of the most intriguing questions in modern astrophysics. Supermassive black holes stand as some of the most enigmatic and powerful objects in the universe, lurking at the centers of most, if not all, large galaxies. These cosmic titans, with masses ranging from millions to billions of times that of our Sun, play a crucial role in shaping the evolution of their host galaxies and the large-scale structure of the universe. The study of supermassive black holes represents a frontier in astrophysics, challenging our understanding of fundamental physics and offering insights into the most extreme environments in the cosmos. The discovery and confirmation of supermassive black holes is a testament to the power of modern astronomical observations and theoretical physics. The concept of black holes, regions of space-time where gravity is so strong that nothing, not even light, can escape, was first proposed as a theoretical possibility arising from Einstein's general theory of relativity. However, the existence of black holes with masses millions or billions of times that of the Sun was not seriously considered until the mid-20th century. The first hints of these cosmic behemoths came from observations of quasars in the 1960s. These incredibly bright and distant objects defied explanation until it was proposed that they were powered by the accretion of matter onto supermassive black holes at the centers of galaxies. This hypothesis was supported by the discovery of rapid variations in quasar brightness, indicating that the source of their power must be contained within a very small volume. As observational techniques improved, astronomers began to find evidence for massive, compact objects at the centers of nearby galaxies as well. The motion of stars and gas near the centers of galaxies revealed the gravitational influence of unseen masses far too large and dense to be explained by normal stellar populations. One of the most compelling pieces of evidence came from our own Milky Way galaxy. Decades of observations of stars orbiting the galactic center revealed the presence of a compact object with a mass of about 4 million solar masses, now known as Sagittarius A. The definitive proof of the existence of supermassive black holes came in 2019, with the first direct image of a black hole's event horizon, captured by the Event Horizon Telescope, EHT. This groundbreaking observation, focused on the supermassive black hole at the center of the galaxy M87, provided visual confirmation of the theories that had been developed over decades. The image showed a bright ring of light surrounding a dark central region, exactly as predicted by models of light bending around a black hole's event horizon. The relationship between supermassive black holes and their host galaxies has become a central topic in astrophysics. One of the most surprising discoveries in this field is the tight correlation between the mass of a galaxy's central black hole and various properties of the galaxy itself, such as the velocity dispersion of stars in the galactic bulge. This relationship, known as the M-sigma relation, suggests a fundamental connection between the growth of supermassive black holes and the evolution of their host galaxies. The mechanism behind this correlation is thought to involve a process called AGN, active galactic nucleus feedback. As material falls onto a supermassive black hole, it forms an accretion disk that heats up to extreme temperatures. This process can release enormous amounts of energy in the form of radiation, winds, and jets of relativistic particles. These outflows can heat or expel gas from the galaxy, regulating star formation and effectively coupling the growth of the black hole to the evolution of its host galaxy. The growth of supermassive black holes over cosmic time is another area of intense study. While we observe fully formed supermassive black holes in quasars at very high redshifts, corresponding to times when the universe was less than 1 billion years old, the mechanism by which these objects grew so large, so quickly, remains a puzzle. Possible explanations include the rapid growth of seed black holes formed from the collapse of early massive stars, the direct collapse of massive gas clouds in the early universe, or the merger of multiple smaller black holes. Observations of relativistic jets from active galactic nuclei provide another window into the physics of supermassive black holes. These jets, which can extend for millions of light years, are thought to be powered by the extraction of rotational energy from the black hole itself through a process known as the Blandford-Znajek mechanism. The study of these jets not only provides insights into black hole physics, but also into the intergalactic medium and the large-scale structure of the universe. Recent technological advancements have revolutionized our ability to study supermassive black holes. In addition to the Event Horizon Telescope, which continues to observe black holes with unprecedented resolution, gravitational wave detectors like LIGO and Virgo are opening up new avenues of investigation. While current detectors are not sensitive to the low-frequency gravitational waves produced by supermassive black hole mergers, future space-based detectors like LISA, Laser Interferometer Space Antenna, promise to observe these events, providing a completely new way to study the growth and evolution of galaxies. The study of supermassive black holes also has profound implications for our understanding of fundamental physics. These objects represent laboratories for testing general relativity in the strong field regime, potentially revealing deviations from Einstein's theory or new physics beyond the standard model. Questions about the nature of singularities, the information paradox, and the compatibility of general relativity with quantum mechanics all come to the fore when considering the physics of supermassive black holes. The role of primordial black holes in the formation of cosmic structures is an area of ongoing research and debate. Some theories propose that black holes formed in the very early universe could have served as seeds for the growth of supermassive black holes and the first galaxies. While the existence of such primordial black holes remains speculative, their potential implications for cosmology and structure formation make them an intriguing area of study. Looking to the future, several key questions about supermassive black holes remain to be answered. How do they form and grow so quickly in the early universe? What is the exact nature of the accretion process that powers active galactic nuclei? How do supermassive black holes affect galaxy evolution on long timescales? Answering these questions will require advancements in both observational capabilities and theoretical modeling. Upcoming observatories promise to push our understanding even further. The James Webb Space Telescope is already providing unprecedented views of the early universe, potentially revealing the first generations of galaxies and their central black holes. Future X-ray missions like Athena will probe the hot gas around supermassive black holes with unprecedented sensitivity, while proposed gravitational wave observatories will open up entirely new ways of studying these objects. In conclusion, supermassive black holes represent one of the most fascinating and important areas of modern astrophysics. From their role in shaping galactic evolution to their status as laboratories for extreme physics, these cosmic titans continue to challenge and expand our understanding of the universe. As we peer deeper into the cosmos and develop more sophisticated tools for observation and analysis, the study of supermassive black holes promises to remain at the forefront of astronomical research for decades to come. As we contemplate the vast scales and extreme physics of supermassive black holes in distant galaxies, it's worth remembering that we too live in a galaxy with its own central black hole. Our home, the Milky Way, offers a unique laboratory for studying galactic structure and evolution up close. Let's turn our attention to this cosmic neighborhood we call home and explore the intricate tapestry of stars, gas, and dark matter that makes up our galactic abode. The Milky Way, our cosmic home, is a vast and complex stellar metropolis that has captivated human imagination for millennia. This grand spiral galaxy, spanning approximately 100,000 light-years in diameter, contains an estimated 100 to 400 billion stars and serves as a cosmic laboratory for understanding galactic structure, evolution, and the intricate interplay of matter and energy on an astronomical scale. As our nearest large galactic neighbor, the Milky Way offers unparalleled opportunities for detailed study, providing insights that shape our understanding of galaxies throughout the universe. The structure of the Milky Way is a testament to the complex forces at play in galactic evolution. At its core lies a dense bulge of older stars, surrounding the supermassive black hole known as Sagittarius A Asca Eta. This central black hole, with a mass of approximately 4 million solar masses, exerts a profound influence on the dynamics of the inner galaxy. Extending outward from the bulge is the galactic disk, a flattened structure roughly 1,000 light-years thick, where the majority of the galaxy's visible matter resides. The disk is home to the iconic spiral arms, regions of increased stellar density and ongoing star formation. The spiral structure of the Milky Way, while difficult to discern from our position within the galaxy, has been mapped through a combination of radio observations, infrared surveys, and careful measurements of stellar motions. Current models suggest that our galaxy possesses 4 major spiral arms: Perseus, Scutum Centaurus, Norma, and Sagittarius. These arms are not static structures, but rather density waves that propagate through the galactic disk, triggering star formation as they compress interstellar gas and dust. Surrounding the visible disk is the galactic halo, a roughly spherical region extending to a radius of at least 100,000 light-years. The halo contains globular clusters, some of the oldest known stellar populations in the universe, as well as a diffuse distribution of stars and hot gas. Beyond the visible halo lies the dark matter halo, an enormous region of invisible matter that dominates the galaxy's mass and extends to at least 1.5 million light-years. The stellar population of the Milky Way is diverse, ranging from newly formed stars in the spiral arms to ancient stars in globular clusters. The distribution of these stars provides crucial information about the galaxy's formation history and evolution. For instance, the galactic disk primarily contains younger, metal-rich stars, while the halo is dominated by older, metal-poor stars. This metallicity gradient offers insights into the process of chemical enrichment over cosmic time. Recent technological advancements have revolutionized our understanding of the Milky Way's structure and composition. The European Space Agency's Gaia mission, launched in 2013, has been particularly transformative. By precisely measuring the positions, distances, and motions of over 1 billion stars, Gaia has provided an unprecedented three-dimensional map of our galaxy. This wealth of data has revealed previously unknown structures, such as stellar streams in the galactic halo, evidence of past mergers with smaller galaxies. At the heart of the Milky Way lies Sagittarius A, the central supermassive black hole. The study of SGAR A has been a triumph of modern astronomy, culminating in the award of the 2020 Nobel Prize in Physics for the discovery of this compact object. Decades of observations, particularly using adaptive optics to track the motions of individual stars orbiting the galactic center, have provided incontrovertible evidence for the presence of a supermassive black hole. In 2022, the Event Horizon Telescope collaboration released the first direct image of SGAR-A seeing, confirming its nature as a black hole and providing a new way to test general relativity in the strong field regime. The interstellar medium, ISM, of the Milky Way plays a crucial role in the galaxy's evolution and star formation processes. This tenuous mixture of gas and dust exists in various phases, from cold molecular clouds where stars are born to hot, ionized regions heated by supernovae and stellar winds. The study of the ISM has been greatly advanced by radio astronomy, which can penetrate the dust that obscures much of the galaxy at visible wavelengths. Surveys such as the HI4PI project have mapped the distribution of neutral hydrogen throughout the galaxy, revealing the complex structure of the ISM and its connection to star formation. The Milky Way's interaction with its galactic environment is an area of ongoing research. Our galaxy is part of the Local Group, a collection of galaxies dominated by the Milky Way and the Andromeda Galaxy, M31. Smaller satellite galaxies, such as the Large and Small Magellanic Clouds, orbit the Milky Way and are gradually being disrupted by its gravitational pull. These interactions leave behind stellar streams and contribute to the growth of the galactic halo. On a larger scale, the Local Group is part of the Laniakea supercluster, a vast network of galaxies and galaxy clusters spanning hundreds of millions of light-years. One of the most significant recent discoveries regarding the Milky Way's history is the identification of the Gaia-Enceladus merger event. Approximately 10 billion years ago, a dwarf galaxy roughly the size of the Small Magellanic Cloud collided with the proto-Milky Way. This collision dramatically altered the structure of our galaxy, contributing to the formation of the thick disk and leaving behind a population of stars with distinct kinematic properties. The ability to reconstruct such ancient events demonstrates the power of modern astronomical techniques and provides crucial insights into the process of galaxy formation and evolution. The study of the Milky Way has profound implications for our understanding of fundamental physics. The distribution of dark matter in the galaxy, inferred from the motions of stars and gas, provides essential constraints on the nature of this mysterious substance. Similarly, the galactic center serves as a unique laboratory for testing general relativity and searching for new physics. Observations of pulsars near SGAR-A, planned for future radio telescopes, may allow for unprecedented tests of strong field gravity. Looking to the future, several key questions about the Milky Way remain to be answered. What is the exact shape and extent of the dark matter halo? How do the magnetic fields threading the galaxy influence its evolution? What is the detailed history of the galaxy's assembly, including past mergers and interactions? Addressing these questions will require continued advancements in observational capabilities and theoretical modeling. Upcoming missions and facilities promise to push our understanding even further. The Vera C. Rubin Observatory, with its Legacy Survey of Space and Time, LSST, will provide a deep, wide-field survey of the southern sky, potentially revealing faint structures in the galactic halo and signs of past mergers. The James Webb Space Telescope is poised to study the galactic center with unprecedented sensitivity and resolution in the infrared, potentially revealing new details about the environment around SGR-A-Ra. In the more distant future, proposed missions like LISA, Laser Interferometer Space Antenna, may detect gravitational waves from the inspiral of compact objects around the central black hole, opening a new window on the dynamics of the galactic center. In conclusion, the Milky Way stands as our cosmic home and a frontier of astronomical research. From its spiral arms to its central black hole, from its oldest stars to its newest, our galaxy offers a unique laboratory for understanding the processes that shape the universe. As we continue to unravel its mysteries, we not only learn about our place in the cosmos, but also gain insights that inform our understanding of galaxies throughout the universe. The study of the Milky Way remains a cornerstone of modern astronomy, bridging the gap between the infinitesimal world of fundamental particles and the vast scales of cosmic structure. As we contemplate the visible majesty of our home galaxy, we are reminded that much of its mass and structure is governed by an invisible component. This unseen influence, known as dark matter, extends far beyond the visible disk of the Milky Way and plays a crucial role in shaping not just our galaxy, but the entire cosmic web. Let us now turn our attention to this enigmatic substance and explore its profound impact on galactic dynamics and the evolution of the universe at large. Dark matter, an enigmatic substance that permeates the universe, plays a crucial role in the formation, structure, and evolution of galaxies. This invisible component, which does not emit, absorb, or reflect light, interacts with ordinary matter primarily through gravity, shaping the cosmic landscape on scales ranging from individual galaxies to the largest structures in the observable universe. The study of dark matter in galaxies represents one of the most intriguing and challenging frontiers in modern astrophysics, offering insights into fundamental physics and cosmology. The concept of dark matter emerged in the 1930s when astronomer Fritz Zwicky observed that the velocities of galaxies in the Coma cluster were far too high to be explained by the visible mass alone. This missing mass problem remained a curiosity for decades until the 1970s, when Vera Rubin and Kent Ford's groundbreaking work on galactic rotation curves brought it to the forefront of astrophysical research. Their observations of spiral galaxies revealed that the outer regions of these cosmic whirlpools were rotating much faster than could be accounted for by the visible matter, suggesting the presence of a vast, invisible halo of matter extending far beyond the visible disk. These galactic rotation curves provide some of the most compelling evidence for dark matter on galactic scales. In a spiral galaxy, the rotational velocity of stars and gas should decrease with distance from the center, following a Keplerian decline similar to that observed in the solar system. However, observations consistently show that rotation curves remain flat or even increase slightly at large radii. This discrepancy can be elegantly explained by the presence of a dark matter halo that extends well beyond the visible disk, providing the additional gravitational force needed to maintain the high rotational velocities. The distribution of dark matter in galaxies is typically modeled using various density profiles, with the Navarro-Frank-White NFW profile being one of the most widely used. This profile, derived from cosmological simulations, predicts that dark matter density increases towards the center of a galaxy, forming a cuspy inner region. However, observations of some galaxies, particularly dwarf galaxies, suggest a more constant density core in their centers, leading to the cusp core problem. one of several challenges to the standard cold dark matter model. Numerical simulations of galaxy formation incorporating dark matter have been instrumental in advancing our understanding of galactic evolution. These simulations, such as the Illustris and Eagle projects, model the growth of cosmic structure from the early universe to the present day, taking into account the gravitational interactions of dark matter and the complex baryonic physics of gas and stars. These computational models have successfully reproduced many observed properties of galaxies and large-scale structure, providing strong support for the dark matter paradigm. However, challenges remain. The missing satellites problem refers to the discrepancy between the number of satellite galaxies predicted by simulations and the number actually observed around the Milky Way and other large galaxies. While recent discoveries of ultra-faint dwarf galaxies have partially alleviated this tension, it remains an active area of research. Similarly, the too big to fail problem points to a mismatch between the predicted and observed internal dynamics of the most massive satellite galaxies. These challenges have led to the exploration of alternative dark matter models, such as warm dark matter or self-interacting dark matter, which could potentially resolve some of these discrepancies while maintaining the overall success of the dark matter paradigm in explaining large-scale structure. Additionally, some researchers have proposed modifications to gravity itself, such as modified Newtonian dynamics, MOND, as alternatives to dark matter. While these theories can explain some galactic-scale observations, they struggle to account for phenomena on larger scales, such as gravitational lensing by galaxy clusters. The search for dark matter particles represents one of the most ambitious endeavors in modern physics. A wide range of experiments are currently underway, seeking to detect dark matter through various means. Direct detection experiments, such as Xenon 1T and Lux Zeppelin, search for rare interactions between dark matter particles and ordinary matter deep underground. Indirect detection experiments, like the Fermi Gamma Ray Space Telescope, look for signs of dark matter annihilation or decay in astrophysical settings. Meanwhile, particle colliders like the Large Hadron Collider at CERN attempt to produce dark matter particles in high-energy collisions. Despite these extensive efforts, dark matter particles have thus far eluded direct detection. This has led to the exploration of a wider range of dark matter candidates, from axions to primordial black holes, each with its own set of theoretical motivations and experimental signatures. The continued non-detection of dark matter particles has also spurred the development of new detection techniques and the proposal of more sensitive experiments for the future. Recent advancements in observational techniques have provided new ways to probe the distribution of dark matter in galaxies. Gravitational lensing, the bending of light by massive objects, allows astronomers to map the total mass distribution of galaxies and clusters, including their dark matter component. Weak lensing surveys, such as the Dark Energy Survey and the upcoming Vera-C, Rubin Observatory's Legacy Survey of Space and Time, promise to provide unprecedented maps of the dark matter distribution on cosmic scales. The study of dark matter in galaxies has profound implications for our understanding of cosmic structure formation and evolution. The hierarchical model of galaxy formation, in which small dark matter halos merge to form progressively larger structures, provides a framework for understanding the growth of galaxies over cosmic time. This model predicts that galaxies should be surrounded by a wealth of substructure in their dark matter halos, some of which may be detectable through careful observations of stellar streams and satellite galaxies. The interplay between dark matter and baryonic matter in galaxies is a complex and ongoing area of research. While dark matter provides the gravitational scaffolding for galaxy formation, baryonic processes such as star formation, supernova feedback, and active galactic nuclei can significantly influence the distribution of both dark and ordinary matter within galaxies. Understanding these feedback mechanisms and their impact on galactic structure is crucial for reconciling observations with theoretical predictions. Looking to the future, several key questions about dark matter in galaxies remain to be answered. What is the nature of dark matter particles? How do they interact with themselves and with ordinary matter? What is the precise distribution of dark matter within galaxies, and how does it vary with galactic mass and environment? Addressing these questions will require continued advancements in observational capabilities, theoretical modeling, and experimental techniques. Upcoming missions and facilities promise to push our understanding even further. The Euclid Space Telescope, set to launch in the near future, will map the distribution of dark matter on cosmic scales with unprecedented precision. The James Webb Space Telescope will probe the formation of the first galaxies, potentially shedding light on the role of dark matter in the early universe. In the more distant future, proposed experiments like Darwin aim to achieve the sensitivity needed to detect or rule out a wide range of dark matter candidates. In conclusion, the study of dark matter in galaxies stands at the intersection of astrophysics, cosmology, and particle physics, offering a unique window into the fundamental nature of the universe. From its role in shaping the largest structures in the cosmos to its influence on the dynamics of individual galaxies, dark matter continues to challenge our understanding and drive scientific innovation. As we continue to probe the dark sector, we not only advance our knowledge of the universe, but also push the boundaries of physics itself, potentially uncovering new fundamental principles that govern the cosmos. As we contemplate the vast, unseen halos of dark matter that envelop galaxies, our gaze inevitably turns to the smallest and most numerous galactic systems in the universe. Dwarf galaxies and satellite galaxies, often orbiting larger galaxies like our own Milky Way, offer unique laboratories for studying dark matter, star formation, and galactic evolution on the smallest scales. These diminutive cosmic systems hold clues to the early universe and the process of galaxy formation, serving as crucial tests for our theories of dark matter and cosmic structure formation. Dwarf galaxies and satellite galaxies represent the most numerous and smallest galactic systems in the universe, serving as fundamental building blocks in the cosmic hierarchy of structure. These diminutive stellar systems, ranging from a few thousand to several billion stars, play a crucial role in our understanding of galaxy formation, evolution, and the nature of dark matter. As satellites orbiting larger galaxies or existing in isolation, dwarf galaxies offer unique insights into the early universe and the processes that have shaped cosmic structure over billions of years. The classification of dwarf galaxies encompasses a diverse range of objects, including dwarf spheroidals, dwarf irregulars, dwarf ellipticals, and ultra-faint dwarfs. Each type exhibits distinct characteristics in terms of morphology, gas content, star formation history, and dark matter distribution. Dwarf spheroidals, for instance, are gas-poor systems with little to no ongoing star formation, while dwarf irregulars often contain significant gas reservoirs and display active star formation. The diversity among dwarf galaxies reflects the various evolutionary paths these systems can take, influenced by both internal processes and environmental factors. The study of dwarf galaxies has a rich history dating back to the early 20th century. The discovery of the Sculptor and Fornax dwarf spheroidal galaxies by Harlow Shapley in the 1930s marked the beginning of systematic investigations into these small galactic systems. However, it wasn't until the advent of modern observational techniques and deep sky surveys that the true abundance and diversity of dwarf galaxies began to be revealed. The Sloan Digital Sky Survey, in particular, led to the discovery of numerous ultra-faint dwarf galaxies around the Milky Way, dramatically increasing the known satellite population of our galaxy. One of the most intriguing aspects of dwarf galaxies is their role as probes of dark matter on small scales. These systems are often dominated by dark matter, with mass-to-light ratios that can exceed 1,000 in some cases. This makes them ideal laboratories for testing theories of dark matter and galaxy formation. The internal dynamics of dwarf galaxies, as revealed by stellar velocity dispersions, provide crucial constraints on the distribution of dark matter within these systems. However, observations of some dwarf galaxies have led to puzzles, such as the too big to fail problem, where the most massive predicted subhalos in simulations appear to be too dense to host the brightest observed satellite galaxies. The interaction between dwarf galaxies and their larger host galaxies is a key area of study in galactic evolution. Satellite galaxies orbiting within the dark matter halo of a massive galaxy like the Milky Way are subject to various environmental effects that can dramatically alter their properties. Tidal stripping, for instance, can remove stars and dark matter from the outer regions of a dwarf galaxy, potentially leading to the formation of stellar streams. Ram pressure stripping, caused by the satellite's motion through the host galaxy's hot gas halo, can remove the dwarf's gas content, quenching star formation. These processes play a crucial role in shaping the observed properties of satellite galaxies and contribute to the growth and evolution of their host galaxies. Recent technological advancements have revolutionized our ability to study dwarf and satellite galaxies. High-resolution spectroscopy on large telescopes allows for precise measurements of stellar velocities in these faint systems, revealing their internal dynamics and dark matter content. The Gaia mission, with its unprecedented astrometric precision, has provided a three-dimensional view of the Milky Way's satellite system, allowing for detailed studies of their orbits and histories. Future facilities like the Vera C. Rubin Observatory promise to discover many more faint dwarf galaxies, potentially revealing the full extent of the local group's dwarf galaxy population. The study of star formation in dwarf galaxies provides crucial insights into the processes that govern galaxy evolution on the smallest scales. Many dwarf galaxies, particularly dwarf irregulars, serve as analogues to the earliest galaxies in the universe, offering a glimpse into the conditions of primordial star formation. The low metallicities observed in many dwarf galaxies make them excellent laboratories for studying star formation in environments similar to those in the early universe. Understanding how star formation proceeds in these low-mass systems is crucial for models of galaxy formation and evolution. One of the most challenging aspects of dwarf galaxy research is reconciling observations with theoretical predictions from cosmological simulations. The MEDI missing satellites and problem, first identified in the late 1990s, highlights the discrepancy between the number of dark matter subhalos predicted by simulations and the observed number of satellite galaxies around the Milky Way. While the discovery of ultra-faint dwarfs has partially alleviated this tension, understanding the full extent of the discrepancy and its implications for our models of structure formation remains an active area of research. The chemical evolution of dwarf galaxies provides a window into the history of chemical enrichment in the universe. Due to their small sizes and relatively simple star formation histories, dwarf galaxies often preserve clear signatures of past star formation and enrichment events. Detailed spectroscopic studies of individual stars in nearby dwarf galaxies have revealed complex enrichment patterns, providing insights into the earliest generations of stars and the processes that have distributed heavy elements throughout the cosmos. The role of dwarf galaxies in rionization, the process by which the universe became transparent to ultraviolet light in its first billion years, is an area of active research. Some models suggest that the earliest dwarf galaxies may have played a significant role in providing the ionizing photons necessary for reionization. Studying the star formation histories of local dwarf galaxies can provide constraints on their potential contributions to this crucial epoch in cosmic history. Dwarf galaxies also serve as important test beds for alternative theories of gravity. Modified Newtonian dynamics, MOND, and other modified gravity theories have been proposed as alternatives to dark matter to explain galactic dynamics. The extreme dark matter dominance observed in many dwarf galaxies makes them crucial testing grounds for these theories as they push the predictions of modified gravity to their limits. Looking to the future, several key questions about dwarf and satellite galaxies remain to be answered. What is the full extent of the dwarf galaxy population in the local group and beyond? How do the smallest galaxies form and evolve over cosmic time? What can the internal structure of dwarf galaxies tell us about the nature of dark matter? Addressing these questions will require continued advancements in observational capabilities and theoretical modeling. Upcoming missions and facilities promise to push our understanding even further. The James Webb Space Telescope will be able to study the stellar populations of nearby dwarf galaxies with unprecedented detail, potentially revealing their full star formation histories. The Vera C. Rubin Observatory's Legacy Survey of Space and Time will discover and characterize countless faint dwarf galaxies, dramatically expanding our census of these systems. In the more distant future, next-generation 30-meter class telescopes will allow for detailed spectroscopic studies of individual stars in dwarf galaxies beyond the local group, opening new frontiers in galactic archaeology. In conclusion, dwarf and satellite galaxies stand as crucial pieces in the cosmic puzzle, offering unique insights into the processes of galaxy formation, the nature of dark matter, and the evolution of the universe on the smallest scales. From their role as building blocks in the hierarchical model of galaxy formation to their status as probes of fundamental physics, these diminutive galactic systems continue to challenge and expand our understanding of the cosmos. As we continue to push the boundaries of observation and theory, the study of dwarf galaxies promises to remain at the forefront of astrophysical research, potentially holding the keys to some of the most fundamental questions in modern cosmology. As we consider the complex interplay between dwarf galaxies and their larger counterparts, we are reminded of the dynamic nature of galactic evolution. This cosmic dance of matter and energy extends beyond individual galaxies to the very fabric of the universe itself. The chemical evolution of galaxies, a process that spans cosmic time and shapes the very composition of the stars, planets, and life as we know it, offers a fascinating window into the history and future of our universe. Let us now turn our attention to this grand cosmic narrative of element creation and distribution throughout the galaxies. The chemical evolution of galaxies is a grand cosmic narrative that spans the entire history of the universe, from the pristine simplicity of the early cosmos to the rich complexity of the present day. This process, which encompasses the creation, distribution, and recycling of chemical elements, is fundamental to our understanding of galaxy formation and evolution, star formation, and ultimately, the origins of life itself. The study of galactic chemical evolution provides a unique window into the history of the universe, tracing the buildup of heavy elements from the first stars to the diverse ecosystems of modern galaxies. At its core, the chemical evolution of galaxies is driven by stellar nucleosynthesis, the process by which stars create heavier elements from lighter ones through nuclear fusion. This concept was first proposed in the seminal paper Synthesis of the Elements in Stars by Burbidge, Fowler, and Hoyle in 1957, often referred to as the B2FH paper. This groundbreaking work laid the foundation for our understanding of how the elements are created in stellar interiors and dispersed into the interstellar medium. The story of galactic chemical evolution begins with the Big Bang, which produced primarily hydrogen and helium, along with trace amounts of lithium and beryllium, all heavier elements, collectively known as metals in astronomical parlance, were forged in the hearts of stars or in violent stellar explosions. The first generation of stars, known as Population 3 stars, formed from this primordial material. These massive, metal-free stars lived short but crucial lives, synthesizing the first heavy elements and dispersing them into their surroundings when they exploded as supernovae. The cycle of star formation, stellar evolution, and element production forms the basis of galactic chemical evolution. As stars form from interstellar gas, they incorporate the metals present in that gas. Throughout their lives, stars fuse lighter elements into heavier ones in their cores. Low and intermediate mass stars primarily produce carbon, nitrogen, and elements created through the slow neutron capture process, S process, such as barium and lead. Massive stars, on the other hand, can produce elements up to iron through fusion in their cores, and even heavier elements through the rapid neutron capture process, R process, during their explosive deaths as supernovae. When stars die, they return a portion of their material, enriched with newly synthesized elements, back to the interstellar medium. This enriched material then becomes part of the raw material for the next generation of stars, leading to a gradual increase in the overall metallicity of the galaxy over time. This process is often referred to as the cosmic cycle of matter, or the galactic fountain, highlighting the continuous exchange of material between stars and the interstellar medium. The chemical evolution of galaxies is not a uniform process but varies significantly depending on the type and environment of the galaxy. Elliptical galaxies, for instance, typically show a rapid early enrichment followed by passive evolution, resulting in an old, metal-rich stellar population. Spiral galaxies, on the other hand, exhibit ongoing star formation and a more gradual enrichment over time, leading to a mix of stellar populations with varying ages and metallicities. One of the key tools in studying galactic chemical evolution is the analysis of elemental abundance patterns in stars and gas. High-resolution spectroscopy allows astronomers to measure the abundances of various elements in individual stars, providing a detailed chemical fingerprint. By studying stars of different ages within a galaxy, researchers can reconstruct the chemical enrichment history of that system. This field, known as galactic archaeology, has been revolutionized by large-scale spectroscopic surveys such as APOG, GALA, and the Gaia ESO survey, which have provided abundance measurements for hundreds of thousands of stars in the Milky Way. The concept of metallicity gradients in galaxies is crucial to understanding their chemical evolution. Most spiral galaxies, including the Milky Way, show a decrease in metallicity from the center to the outskirts. These gradients are shaped by a complex interplay of factors, including the history of star formation, gas inflow and outflow, and radial migration of stars and gas. The study of metallicity gradients provides insights into the formation history of galaxies and the processes that drive their evolution. Recent advancements in observational techniques have allowed for unprecedented insights into the chemical evolution of galaxies. Integral field spectroscopy, as employed by surveys like CALIPER and MANGA, provides spatially resolved spectroscopic data for thousands of nearby galaxies, allowing for detailed studies of chemical abundance distributions across entire galactic disks. At the same time, observations of high redshift galaxies with facilities like ALMA are pushing our understanding of chemical evolution to earlier cosmic epochs, revealing how galaxies were enriched in their formative stages. The role of gas flows in shaping galactic chemical evolution has become increasingly recognized in recent years. Inflows of pristine or metal-poor gas from the intergalactic medium can dilute the metallicity of a galaxy, while outflows driven by supernovae or active galactic nuclei can expel metal-enriched material. These processes, collectively known as the baryon cycle, play a crucial role in regulating the chemical evolution of galaxies and connecting them to their larger cosmic environment. One of the most challenging aspects of studying galactic chemical evolution is understanding the relative contributions of different nucleosynthetic sources. While the origins of some elements are well understood, others remain puzzling. The production sites of our process elements, for instance, have been a long-standing mystery. The detection of gravitational waves from a neutron star merger in 2017, accompanied by observations of associated R-process element production, provided strong evidence for these events as significant sources of heavy elements. However, the full picture of R-process element production in galaxies is still being pieced together. The chemical evolution of galaxies has profound implications for our understanding of cosmic history and the origins of life. The elements created through stellar nucleosynthesis and distributed through galactic chemical evolution are the same elements that make up planets, including Earth and all living organisms. By studying how these elements are produced and distributed throughout galaxies, we gain insights into the conditions necessary for the formation of habitable planets and the potential for life elsewhere in the universe. Looking to the future, several key questions about galactic chemical evolution remain to be answered. How do the first metals produced by population 3 stars influence subsequent galaxy evolution? What is the full inventory of nucleosynthetic sources contributing to galactic enrichment? How do galactic environments and large-scale structure influence chemical evolution? Addressing these questions will require continued advancements in observational capabilities, theoretical modeling, and our understanding of nuclear physics. Upcoming missions and facilities promise to push our understanding even further. The James Webb Space Telescope will probe the chemical composition of the earliest galaxies, potentially revealing the signature of the first stars. Next-generation extremely large telescopes will allow for detailed chemical abundance studies of individual stars in galaxies beyond the local group. In the more distant future, proposed missions like LUVOIR could potentially detect biosignatures in the atmospheres of exoplanets, directly linking galactic chemical evolution to the search for life in the universe. In conclusion, the chemical evolution of galaxies represents a cosmic saga that connects the first moments after the Big Bang to the rich diversity of the present-day universe. This process, driven by the lives and deaths of stars, shapes the composition of galaxies and ultimately provides the raw materials for planets and life. As we continue to unravel the intricacies of galactic chemical evolution, we not only gain insights into the history of our cosmic home, but also deepen our understanding of our place in the universe and the conditions that make life possible. As we contemplate the grand narrative of chemical enrichment that has unfolded over billions of years, we are reminded that galaxies are not isolated islands in the cosmos. The evolution of these vast stellar systems is profoundly influenced by their interactions with one another. Collisions and mergers between galaxies represent some of the most dramatic events in the universe, shaping the structure and composition of galaxies we see today. Let us now turn our attention to these cosmic collisions and explore how they drive the ongoing evolution of galaxies throughout the universe. Galactic collisions and mergers stand as some of the most spectacular and transformative events in the cosmos, playing a crucial role in shaping the evolution and structure of galaxies throughout the universe. These cosmic encounters, which unfold over millions to billions of years, dramatically alter the morphology, star formation rates, and chemical composition of the participating galaxies, leaving an indelible mark on the cosmic landscape. The study of these interactions provides key insights into the formation of large-scale structures, the growth of supermassive black holes, and the overall evolution of galaxies from the early universe to the present day. At its core, the process of galactic collision and merger is driven by the fundamental force of gravity. As galaxies move through space, their mutual gravitational attraction can cause them to approach and eventually interact with one another. The outcome of these interactions depends on various factors, including the masses of the galaxies, their relative velocities, and the geometry of their encounter. Minor mergers involve a large galaxy absorbing a much smaller satellite, while major mergers occur between galaxies of comparable mass. The concept of galactic collisions was first seriously considered in the mid-20th century, with pioneering work by astronomers like Erich Holmberg, who used light bulbs and photocells to simulate gravitational interactions between galaxies. However, it wasn't until the advent of powerful computers in the 1970s and 1980s that detailed simulations of galaxy mergers became possible. The groundbreaking simulations by Ala and Juri Toumre in 1972 demonstrated that many observed galactic structures, such as tidal tails and bridges, could be explained by gravitational interactions between galaxies. One of the most striking effects of galactic collisions is the dramatic transformation of galactic morphology. As galaxies interact, tidal forces distort their shapes, often leading to the formation of long tidal tails and bridges of stars and gas stretching between the galaxies. These tidal features can extend for hundreds of thousands of light years, serving as telltale signs of past or ongoing interactions. In the case of major mergers between spiral galaxies, the end result is often an elliptical galaxy, with the ordered disk structure of the original galaxies destroyed and replaced by a more randomized distribution of stars. The impact of galactic collisions on star formation is profound and multifaceted. As galaxies interact, gravitational torques and tidal forces can funnel large amounts of gas towards the galactic centers, triggering intense bursts of star formation known as starbursts. These episodes of enhanced star formation can increase the star formation rate by factors of 10 to 100 compared to isolated galaxies. Observations of systems like the Antennae galaxies, NGC 4038-4239, reveal numerous regions of intense star formation triggered by their ongoing merger. However, the relationship between mergers and star formation is complex, as some simulations suggest that mergers can also quench star formation in the long term by heating or expelling gas from the galaxies. The role of galactic mergers in the growth of supermassive black holes has become increasingly recognized in recent years. As gas is funneled towards the centers of merging galaxies, it not only fuels star formation, but also feeds the central supermassive black holes. This can trigger periods of intense activity, leading to the formation of active galactic nuclei, AGN, and quasars. The observed correlation between the mass of a galaxy's central black hole and the velocity dispersion of its bulge, the MS relation, is thought to be a consequence of this co-evolution of galaxies and their central black holes through merger events. Simulations of galaxy mergers have played a crucial role in advancing our understanding of these processes. Modern computational models, such as those used in the Illustris and Eagle projects, incorporate a wide range of physical processes, including gravity, gas dynamics, star formation, and feedback from supernovae and AGN. These simulations allow astronomers to study the entire merger process, from the initial approach of the galaxies to the final relaxation of the merger remnant, providing insights that would be impossible to gain from observations alone, given the vast timescales involved. Recent technological advancements have revolutionized our ability to study galactic mergers observationally. The advent of integral field spectroscopy, as employed by surveys like Quasar and Manga, allows astronomers to obtain spatially resolved spectroscopic data across entire galaxies, revealing the dynamics and chemical composition of merging systems in unprecedented detail. In the radio regime, facilities like ALMA provide high-resolution views of the cold gas dynamics in merging galaxies, crucial for understanding the fueling of star formation and AGN activity. The study of galactic mergers extends beyond the local universe. Observations with the Hubble Space Telescope and ground-based adaptive optics systems have revealed that mergers were more common in the early universe, playing a crucial role in the rapid growth of galaxies during the first few billion years after the Big Bang. The higher merger rate in the past is a natural consequence of the hierarchical model of galaxy formation, where large structures form through the successive merging of smaller ones. One of the most challenging aspects of studying galactic mergers is understanding their long-term impact on galaxy evolution. While individual merger events can be identified and studied, tracing the cumulative effect of multiple mergers over cosmic time requires a combination of observations, simulations, and theoretical modeling. The concept of galactic archaeology, which aims to reconstruct the formation history of galaxies by studying their present-day properties, plays a crucial role in this endeavor. The fate of our own Milky Way galaxy is intimately tied to the process of galactic mergers. Observations and simulations indicate that the Milky Way is on a collision course with the nearby Andromeda galaxy, M31, with the merger expected to begin in about 4.5 billion years. This future collision, often dubbed Milkomeda, will dramatically reshape our galactic neighborhood, likely resulting in the formation of a giant elliptical galaxy. While this event is far in the future from a human perspective, it underscores the dynamic and ever-changing nature of the universe. The study of galactic mergers has implications that extend far beyond galaxy evolution. These cosmic collisions play a role in redistributing heavy elements throughout the universe, potentially influencing the chemical composition of future generations of stars and planets. Moreover, the intense star formation triggered by mergers in the early universe may have played a crucial role in cosmic ionization, the process by which the first stars and galaxies ionized the neutral hydrogen that pervaded the early universe. Looking to the future, several key questions about galactic mergers remain to be answered. How do mergers influence the distribution and properties of dark matter halos? What is the full impact of mergers on the evolution of supermassive black holes? How do merger-induced starbursts and AGN activity affect the surrounding intergalactic medium? Addressing these questions will require continued advancements in observational capabilities and theoretical modeling. Upcoming missions and facilities promise to push our understanding even further. The James Webb Space Telescope will provide unprecedented views of merging galaxies in the early universe, potentially revealing the role of mergers in shaping the first galaxies, the Vera C. Rubin Observatory's Legacy Survey of Space and Time will discover and characterize numerous merging systems in the local universe, providing a statistical view of merger rates and properties. In the more distant future, gravitational wave observatories like LISA may detect the mergers of supermassive black holes at the hearts of colliding galaxies, opening a new window on these cosmic collisions. In conclusion, galactic collisions and mergers represent a fundamental process in the evolution of the universe, driving the growth and transformation of galaxies across cosmic time. From shaping the morphology of galaxies to triggering bursts of star formation and fueling the growth of supermassive black holes, these cosmic encounters leave an indelible mark on the fabric of the cosmos. As we continue to study these phenomena, we not only gain insights into the history and future of our own galaxy, but also deepen our understanding of the dynamic and interconnected nature of the universe as a whole. As we contemplate the grand cosmic dance of merging galaxies, our gaze naturally turns to some of the oldest and most enigmatic structures within these galactic systems. Globular clusters, ancient assemblages of stars that orbit in the halos of galaxies, offer a unique window into the early history of galaxy formation and the nature of the first generations of stars. These cosmic fossils, with their tightly packed spherical configurations and populations of ancient stars, hold clues to the conditions present in the early universe and the processes that shape the galaxies we see today. Globular clusters stand as ancient cosmic relics, offering a unique window into the early history of galaxies and the universe itself. These dense, spherical collections of stars, typically containing hundreds of thousands to millions of members, orbit in the halos of galaxies and represent some of the oldest known stellar populations in the universe. With ages ranging from 10 to 13 billion years, globular clusters serve as fossil records of the conditions present during the earliest epochs of galaxy formation, providing crucial insights into stellar evolution, galactic dynamics, and cosmology. The study of globular clusters has a rich history dating back to the 18th century, when Charles Messier and William Herschel first catalogued many of these objects. However, it wasn't until the early 20th century that their true nature and significance began to be understood. Harlow Shapley's groundbreaking work in the 1910s and 1920s used globular clusters to map the structure of the Milky Way, revolutionizing our understanding of our galaxy's size and our place within it. This work laid the foundation for the use of globular clusters as tracers of galactic structure and evolution. Globular clusters are characterized by their compact, roughly spherical shape and high stellar density. At their cores, these clusters can reach densities of thousands of stars per cubic parsec, creating an environment unlike any found elsewhere in the galaxy. This extreme density leads to frequent stellar encounters and interactions, making globular clusters ideal laboratories for studying stellar dynamics and the evolution of dense stellar systems. The formation of globular clusters remains an area of active research and debate. The classical view held that these clusters formed as single bursts of star formation in the early universe, creating a coeval population of stars with nearly identical ages and chemical compositions. However, recent observations have revealed a more complex picture. Many globular clusters show evidence of multiple stellar populations with distinct chemical abundances, suggesting a more prolonged or multi-phase formation process. One of the key characteristics of globular clusters is their low metallicity, a term astronomers use to describe the abundance of elements heavier than helium. The stars in globular clusters typically have metallicities ranging from 110 to 100 of the solar value, reflecting the chemical composition of the early universe from which they formed. This low metallicity makes globular clusters valuable probes of early cosmic chemical evolution and nucleosynthesis. The stellar populations within globular clusters provide a wealth of information about stellar evolution. Because all the stars in a cluster formed at roughly the same time from the same material, Globular clusters present a snapshot of stellar evolution for a single age and metallicity. This makes them invaluable for testing and refining models of stellar evolution. The observation of features such as the main sequence turnoff, horizontal branch, and blue stragglers in globular cluster color magnitude diagrams has been crucial in advancing our understanding of stellar life cycles. Recent technological advancements have revolutionized the study of globular clusters. The Hubble Space Telescope has provided unprecedented views of these dense stellar systems, allowing astronomers to resolve individual stars even in the crowded cores of clusters. Missions like Gaia have provided precise measurements of the positions and motions of stars in nearby globular clusters, revealing their internal dynamics and orbital properties with unprecedented accuracy. One of the most intriguing aspects of globular cluster research is their potential to harbor intermediate mass black holes, IMBHs. These black holes, with masses ranging from hundreds to tens of thousands of solar masses, could represent a missing link between stellar mass black holes and the supermassive black holes found at the centers of galaxies. While definitive evidence for IMBHs in globular clusters remains elusive, several candidates have been identified through careful studies of stellar dynamics and X-ray observations. The distribution of globular clusters around galaxies provides crucial information about galactic formation and evolution. In the Milky Way, globular clusters are concentrated in the galactic halo and bulge, with their spatial and kinematic properties offering clues to the early assembly history of our galaxy. Studies of globular cluster systems in other galaxies have revealed correlations between the number and properties of clusters and the mass and morphology of their host galaxies, providing insights into the processes of galaxy formation and evolution. The use of globular clusters as standard candles for measuring cosmic distances has been an important application in extragalactic astronomy. The luminosity function of globular clusters, particularly the peak of this function known as the globular cluster luminosity function, GCLF, has been found to be remarkably consistent across different galaxies. This property allows astronomers to use globular clusters to estimate distances to galaxies beyond the reach of other standard candle methods. Recent discoveries have challenged some long-held assumptions about globular clusters. The detection of multiple stellar populations within individual clusters has forced a re-evaluation of formation models. Some clusters show evidence of extended star formation histories or self-enrichment processes, suggesting a more complex formation scenario than previously thought. Additionally, the discovery of young massive clusters in nearby galaxies, which may represent proto-globular clusters, is providing new insights into the formation conditions of these ancient systems. The study of globular clusters extends beyond our own galaxy. Observations of globular cluster systems in other galaxies, from nearby dwarf galaxies to distant giant ellipticals, offer a comparative view that informs our understanding of galaxy formation and evolution. The Hubble Space Telescope has been instrumental in these studies, allowing for the detection and characterization of globular clusters in galaxies tens of millions of light-years away. The chemical composition of stars in globular clusters provides a unique window into the nucleosynthesis processes of the early universe. Detailed spectroscopic studies have revealed peculiar abundance patterns, such as the so-called sodium-oxygen anti-correlation, which are not typically seen in field stars. These patterns offer clues to the environments in which these clusters formed and the types of stars that enrich them. Looking to the future, several key questions about globular clusters remain to be answered. How exactly did these ancient systems form, and what do their properties tell us about the conditions in the early universe? What is the full extent of their role in the assembly history of galaxies? Do they indeed harbor intermediate mass black holes? And if so, what are the implications for our understanding of black hole formation and growth? Upcoming missions and facilities promise to push our understanding even further. The James Webb Space Telescope will be able to study globular clusters in unprecedented detail, potentially resolving individual stars in clusters in nearby galaxies and probing the stellar populations of the most distant known clusters. Next-generation ground-based extremely large telescopes will provide high-resolution spectroscopy of individual stars in clusters, offering new insights into their chemical composition and internal dynamics. In conclusion, globular clusters stand as cosmic time capsules, preserving information about the earliest epochs of galaxy formation and stellar evolution. From their role in mapping the structure of our galaxy to their use as probes of the early universe, these ancient stellar systems continue to be at the forefront of astronomical research. As we continue to study these fascinating objects, we not only learn about the history of our cosmic neighborhood, but also gain insights into the fundamental processes that have shaped the universe over billions of years. As we contemplate the ancient stellar populations of globular clusters, our attention is drawn to another class of energetic phenomena that illuminate the cosmos: active galactic nuclei and quasars. These extraordinarily luminous objects, powered by supermassive black holes at the centers of galaxies, represent some of the most extreme and energetic processes in the universe. Let us now turn our gaze to these cosmic beacons and explore how they shape our understanding of galactic evolution and the nature of the most massive black holes in the universe. Active galactic nuclei, AGN, and quasars represent some of the most energetic and luminous phenomena in the universe, serving as cosmic beacons that illuminate our understanding of galactic evolution, supermassive black holes, and the early universe. These extraordinary objects, powered by the accretion of matter onto supermassive black holes at the centers of galaxies, can outshine their entire host galaxies and emit radiation across the entire electromagnetic spectrum. The study of AGN and quasars has revolutionized our view of the cosmos, providing insights into the growth of galaxies, the properties of supermassive black holes, and the conditions present in the early universe. The discovery of quasars in the early 1960s marked a pivotal moment in astronomy. Initially detected as radio sources with star-like optical counterparts, these objects defied explanation until their spectra revealed enormous redshifts, indicating vast distances and incredible luminosities. The term quasar, short for quasi-stellar radio source, reflects their star-like appearance in optical images despite their extragalactic nature. As observations improved, it became clear that quasars represent the most extreme examples of a broader class of objects known as active galactic nuclei. At the heart of every AGN lies a supermassive black hole, typically with a mass ranging from millions to billions of times that of the Sun. The incredible energy output of these objects is powered by the accretion of matter onto these black holes. As material falls towards the black hole, it forms an accretion disk, a flattened structure where gravitational energy is converted into thermal energy through viscous processes. The inner regions of these accretion disks can reach temperatures of millions of degrees Celsius, causing them to emit intense radiation across the electromagnetic spectrum, from radio waves to X-rays and even gamma rays. The unified model of AGN, developed in the 1980s and 1990s, proposes that the diverse observational classes of AGN can be explained by a common underlying structure viewed from different angles. This model includes a central black hole surrounded by an accretion disk, a region of rapidly moving gas clouds that produce broad emission lines, the broadline region, a dusty torus that can obscure the central regions, and, in some cases, powerful jets of relativistic particles extending far beyond the host galaxy. The orientation of this structure relative to our line of sight determines the observed properties of the AGN, explaining the various subclasses such as Seyfert galaxies, radio galaxies, and blazars. One of the most remarkable features of some AGN is the presence of relativistic jets. These collimated outflows of plasma, accelerated to speeds approaching that of light, can extend for hundreds of thousands or even millions of light years. The mechanism behind the formation and collimation of these jets remains an active area of research, with magnetic fields playing a crucial role. The interaction of these jets with the surrounding intergalactic medium creates vast radio-emitting lobes, making radio galaxies some of the largest known single objects in the universe. The study of AGN and quasars has been revolutionized by multi-wavelength observations. X-ray observatories like Chandra and XMM Newton have provided unprecedented views of the hot gas in AGN, revealing complex structures and variability. In the radio regime, very long baseline interferometry (VLBI) techniques have allowed for incredibly detailed imaging of jets, showing their structure and evolution over time. The Fermi Gamma Ray Space Telescope has revealed that AGN are among the most powerful sources of high-energy gamma rays in the universe. One of the most significant discoveries in recent years has been the observation of rapid variability in AGN across multiple wavelengths. This variability, sometimes occurring on timescales of hours or even minutes, provides crucial information about the size and structure of the emitting regions. The technique of reverberation mapping, which measures the time delay between variations in the continuum emission and the response of the broadline region, has allowed astronomers to estimate the masses of supermassive black holes in distant AGN. The relationship between AGN activity and galaxy evolution has become a central theme in modern astrophysics. Observations have revealed a tight correlation between the mass of a galaxy's central black hole and the velocity dispersion of stars in its bulge, known as the MS relation. This suggests a fundamental connection between the growth of supermassive black holes and the evolution of their host galaxies. AGN feedback, the process by which energy and momentum from the AGN affects the surrounding galaxy, is now recognized as a crucial factor in regulating star formation and the overall evolution of galaxies. Quasars, being the most luminous sustained sources of electromagnetic radiation in the universe, serve as cosmic lighthouses that illuminate the distant universe. Their extreme brightness allows them to be detected at vast distances, with the most distant known quasars observed at redshifts greater than 7, corresponding to a time when the universe was less than 1 billion years old. These high redshift quasars provide crucial information about the early stages of galaxy and black hole formation, the process of cosmic reionization, and the chemical enrichment of the early universe. The study of quasar absorption lines has opened a unique window into the distribution and properties of gas in the intergalactic medium. As light from distant quasars travels through space, it is absorbed by intervening gas clouds, leaving characteristic imprints in the quasar's spectrum. This technique has allowed astronomers to map the distribution of neutral hydrogen through cosmic time, tracing the process of reionization and the growth of cosmic structure. Recent technological advancements have pushed the boundaries of AGN research. Adaptive optics systems on large ground-based telescopes have allowed for high-resolution imaging of nearby AGN, revealing the complex structures in their host galaxies. The Event Horizon Telescope, a global network of radio telescopes, achieved the first direct imaging of a supermassive black hole's shadow in the galaxy M87, providing a dramatic confirmation of general relativity in the strong field regime. Looking to the future, several key questions about AGN and quasars remain to be answered. How did the first supermassive black holes form? And how did they grow so quickly in the early universe? What is the exact mechanism behind the launching and collimation of relativistic jets? How does AGN feedback precisely affect galaxy evolution over cosmic time? Addressing these questions will require continued advancements in observational capabilities and theoretical modeling. Upcoming missions and facilities promise to push our understanding even further. The James Webb Space Telescope will provide unprecedented views of distant quasars and their host galaxies, potentially revealing the seeds of the first supermassive black holes. Next-generation X-ray observatories like Athena will probe the hot gas around AGN with unprecedented sensitivity, offering new insights into accretion processes and feedback mechanisms. In the more distant future, gravitational wave observatories like LISA may detect the mergers of supermassive black holes, opening a new window on the growth of these cosmic titans. In conclusion, the study of active galactic nuclei and quasars stands at the intersection of multiple fields in astrophysics, connecting the physics of black holes to the evolution of galaxies and the structure of the universe itself. These cosmic powerhouses continue to challenge our understanding, driving innovations in observational techniques and theoretical modeling. As we continue to unravel their mysteries, we not only learn about these extreme objects but also gain insights into the fundamental processes that have shaped the universe over billions of years. As we contemplate the energetic phenomena of AGN and quasars, our attention is drawn to the vast expanses between galaxies. The intergalactic medium, far from being empty space, is a complex and dynamic environment that plays a crucial role in the evolution of galaxies and the universe as a whole. This tenuous cosmic web of gas and dark matter serves as both the source of material for galaxy growth and the repository for galactic outflows, linking the smallest scales of star formation to the largest structures in the cosmos. Let us now turn our gaze to this cosmic web and explore how it shapes the evolution of galaxies and the distribution of matter in the universe. The galactic interstellar medium, ISM, represents a complex and dynamic ecosystem that plays a crucial role in the life cycle of galaxies. Far from being empty space, the ISM is a rich tapestry of gas, dust, and energetic particles that permeates the space between stars within a galaxy. This multifaceted environment serves as both the birthplace of new stars and the repository for the material ejected by dying stars, forming a cosmic cycle that drives galactic evolution and shapes the observable universe. The study of the interstellar medium has its roots in the early 20th century, with the discovery of stationary absorption lines in stellar spectra by Johannes Hartmann in 1904. These lines, originating from calcium ions in interstellar space, provided the first evidence for the existence of matter between stars. Over the decades, our understanding of the ISM has grown tremendously, revealing a medium far more complex and influential than initially imagined. The ISM is composed of several distinct phases, each characterized by different temperatures, densities, and ionization states. The coldest and densest phase is the molecular medium, where temperatures can drop to about 10 to 20 Kelvin and densities can reach up to 106 particles per cubic centimeter. This phase, primarily composed of molecular hydrogen, H2, is where star formation occurs. Next is the cold neutral medium, with temperatures around 100 K and densities of about 50 particles per cubic centimeter. The warm neutral medium and warm ionized medium have temperatures of about 8,000 K, but differ in their ionization states. Finally, the hot ionized medium, heated by supernova explosions, can reach temperatures of millions of Kelvin but has very low densities. One of the most important components of the ISM is dust, which, despite making up only about 1% of the ISM's mass, plays a disproportionately large role in galactic processes. Interstellar dust grains, typically less than a micrometer in size, are composed of silicates, carbonaceous materials, and ice mantles. These tiny particles are crucial for the formation of molecular hydrogen, as their surfaces provide sites for atoms to combine. Dust also plays a significant role in the heating and cooling of interstellar gas, and its opacity shapes the radiation field within galaxies. The life cycle of the interstellar medium is intimately connected to the life cycle of stars. Molecular clouds, the densest regions of the ISM, serve as the birthplaces of stars. These clouds, often containing masses equivalent to thousands or even millions of suns, can collapse under their own gravity to form new stars. As these stars evolve, they return material to the ISM through stellar winds and, in the case of massive stars, supernova explosions. This process enriches the ISM with heavy elements, metals in astronomical parlance, produced through stellar nucleosynthesis, gradually changing the chemical composition of the galaxy over cosmic time. The dynamics of the ISM are governed by a complex interplay of gravitational, magnetic, and turbulent forces. Turbulence, in particular, plays a crucial role in shaping the structure of the ISM across a wide range of scales. Observations and simulations suggest that the ISM exhibits a self-similar, fractal-like structure, with turbulent motions cascading from galactic scales down to the scales of individual star-forming regions. This turbulence influences the efficiency of star formation and the distribution of gas densities within the galaxy. Magnetic fields thread through the ISM, influencing its dynamics and structure. These fields, typically on the order of a few microgauss in strength, can provide support against gravitational collapse in molecular clouds, potentially regulating star formation. They also play a role in confining cosmic rays, high-energy particles that permeate the ISM and contribute to its energy balance. The study of the ISM has been revolutionized by advancements in observational techniques across the electromagnetic spectrum. Radio observations, particularly of the 21 semipiral line of neutral hydrogen, have mapped the distribution and kinematics of the atomic ISM in unprecedented detail. Millimeter and sub-millimeter telescopes, such as ALMA, Atacama Large Millimeter Sub-Millimeter Array, probe the cold, dense molecular gas where stars form. In the infrared, space-based observatories like Spitzer and Herschel have revealed the distribution of dust and the processes of star formation hidden from optical view. One of the most significant recent discoveries in ISM research is the prevalence of molecular gas in the early universe. Observations with ALMA and other facilities have detected massive reservoirs of molecular gas in galaxies when the universe was less than 1 billion years old. These findings challenge our understanding of how quickly heavy elements were produced and molecular gas formed in the early stages of galaxy evolution. The interaction between the ISM and galactic structure is a key area of ongoing research. The spiral arms of disk galaxies are not just patterns of stars but are associated with enhancements in gas density and star formation. The exact nature of spiral arms, whether they are density waves propagating through the disk or more transient features, remains a topic of debate. Understanding this interaction is crucial for explaining the observed patterns of star formation in galaxies. Feedback processes play a crucial role in regulating the state of the ISM and, by extension, the evolution of galaxies. Stellar feedback, in the form of winds, radiation, and supernovae, injects energy and momentum into the surrounding ISM, potentially disrupting star-forming regions and driving galactic-scale outflows. On larger scales, feedback from active galactic nuclei, AGN, can heat the ISM and even expel gas from the galaxy, profoundly influencing its evolution. The study of the ISM extends beyond our own galaxy. Observations of the ISM in nearby galaxies provide a comparative view that informs our understanding of galactic evolution. For instance, studies of the large and small Magellanic Clouds, our nearest galactic neighbors, have revealed how the ISM properties and star formation processes differ in lower metallicity environments, potentially analogous to conditions in the early universe. Looking to the future, several key questions about the ISM remain to be answered. How does the multi-phase structure of the ISM emerge and evolve over cosmic time? What determines the efficiency of star formation in molecular clouds? How do galactic-scale processes couple to the small-scale physics of the ISM? Addressing these questions will require continued advancements in observational capabilities and theoretical modeling. Upcoming missions and facilities promise to push our understanding even further. The James Webb Space Telescope will provide unprecedented views of the dusty and molecular ISM in distant galaxies, potentially revealing how the ISM properties evolve over cosmic time. Next-generation radio telescopes, such as the Square Kilometre Array, will map the neutral hydrogen content of galaxies over a significant fraction of cosmic history. In the more distant future, far infrared space observatories may provide detailed views of the cold ISM and star formation processes obscured at other wavelengths. In conclusion, the galactic interstellar medium stands as a crucial component in the cosmic ecosystem, linking the life cycles of stars to the evolution of galaxies as a whole. From its role as the birthplace of stars to its function as a repository for stellar ejecta, the ISM shapes the observable properties of galaxies and drives their evolution over cosmic time. As we continue to study this complex and dynamic medium, we not only deepen our understanding of galactic processes, but also gain insights into the fundamental mechanisms that have shaped the universe over billions of years. As we contemplate the intricate dance of matter and energy within galaxies, our gaze is inevitably drawn outward to the vast cosmic stage upon which these galactic dramas unfold. The early universe, a realm of extreme conditions and rapid change, set the stage for the formation of the first galaxies and the large-scale structure we observe today. Let us now turn our attention to this crucible of cosmic creation, exploring how the first luminous objects emerged from the primordial darkness and shaped the evolution of the universe. Galaxies in the early universe represent some of the most enigmatic and crucial objects in cosmic history, serving as the building blocks for the large-scale structure we observe today. These primordial stellar systems, formed when the universe was less than 1 billion years old, offer a unique window into the conditions present during the cosmic dawn and the processes that shaped the evolution of the universe. The study of these ancient galaxies challenges our understanding of physics, pushes the limits of our observational capabilities, and provides crucial insights into the formation of the first stars, black holes, and heavy elements. The search for galaxies in the early universe is inextricably linked to the quest to understand cosmic reionization, a fundamental phase transition in which the neutral hydrogen that pervaded the universe following recombination was ionized by the first luminous sources. This epoch, occurring roughly between 400 million and 1 billion years after the Big Bang, marks the end of the cosmic dark ages and the emergence of the first galaxies and quasars. The detection and characterization of these early galaxies pose significant observational challenges. As light from these distant objects travels across the expanding universe, it undergoes a substantial redshift, stretching visible light into the infrared part of the spectrum. This necessitates the use of infrared-capable telescopes, both in space and on the ground. The Hubble Space Telescope, particularly with its Wide-Field Camera 3 installed in 2009, has been instrumental in pushing the frontier of high-redshift galaxy observations. Ground-based facilities like the Keck telescopes and the Atacama Large Millimeter Submillimeter Array, ALMA, have also played crucial roles in confirming and characterizing these distant galaxies. One of the most significant breakthroughs in the study of early galaxies came with the implementation of the Lyman break technique. This method, pioneered by Charles Steidl and collaborators in the 1990s, takes advantage of the sharp cutoff in the spectral energy distribution of galaxies at the wavelength of the Lyman limit, 912.0 in the rest frame. By observing in multiple filters, astronomers can identify high redshift galaxy candidates based on their dropout behavior in bluer filters. This technique has been spectacularly successful, leading to the discovery of thousands of galaxies at redshifts greater than 6, corresponding to a time when the universe was less than 1 billion years old. The properties of these early galaxies often defy expectations based on observations of nearby galaxies. Many appear to be forming stars at prodigious rates, sometimes hundreds of times faster than the Milky Way, despite their relatively small sizes. This high star formation efficiency may be due to higher gas fractions, more compact configurations, or different physical conditions in the early universe. The dust content of these galaxies is also a subject of intense study, as the presence of dust implies previous generations of stars and provides clues about early chemical enrichment. One of the most pressing questions in the study of early galaxies is their role in cosmic reionization. Current evidence suggests that star-forming galaxies were the primary source of ionizing photons during this epoch, with a potentially significant contribution from quasars at later times. However, the exact contribution of different sources and the progression of reionization remain active areas of research. The detection of the Gunn-Peterson trough in the spectra of distant quasars, indicating the presence of neutral hydrogen, has provided crucial constraints on the timing of reionization. The formation of the first galaxies is intimately tied to the nature of dark matter and the growth of cosmic structure. In the standard lambda-CDM cosmological model, small density fluctuations in the early universe grow under the influence of gravity, forming dark matter halos that serve as the sites for galaxy formation. Numerical simulations, such as the Illustris and Eagle projects, have played a crucial role in modeling this process and predicting the properties of early galaxies. However, tensions between observations and simulations, particularly regarding the abundance and properties of low-mass galaxies, continue to challenge our understanding. The discovery of extremely luminous galaxies and quasars at redshifts greater than 7 has raised important questions about the growth of supermassive black holes in the early universe. The detection of quasars with billion solar mass black holes, when the universe was less than 1 billion years old, challenges our understanding of black hole formation and growth. Various scenarios, including the direct collapse of massive gas clouds or the rapid growth of stellar mass black hole seeds, have been proposed to explain these observations. Recent technological advancements have revolutionized the study of early galaxies. The advent of multi-object spectrographs on large ground-based telescopes has enabled the efficient spectroscopic confirmation of high redshift galaxy candidates. Gravitational lensing, particularly of massive galaxy clusters, has allowed for the detection of even fainter and more distant galaxies through magnification. The Atacama Large Millimeter Shan Submillimeter Array, ALMA, has provided unprecedented views of dust and gas in early galaxies, revealing complex structures and kinematics. The James Webb Space Telescope, JWST, launched in December 2021, represents a quantum leap in our ability to study the early universe. With its large collecting area, high sensitivity, and infrared capabilities, JWST is poised to detect and characterize galaxies from the epoch of Ryanization and potentially even earlier. Early results from JWST have already pushed the frontier of galaxy detection to unprecedented redshifts, with candidates identified at redshifts greater than 10, corresponding to times when the universe was less than 500 million years old. The study of galaxies in the early universe has profound implications for our understanding of cosmic history and the origins of structure. These observations provide crucial constraints on models of galaxy formation and evolution, the growth of supermassive black holes, and the process of cosmic chemical enrichment. Moreover, they offer insights into the conditions necessary for the formation of galaxies like our own Milky Way and the potential for life in the universe. Looking to the future, several key questions about early galaxies remain to be answered. What were the properties of the very first galaxies, and how did they influence their environments? How did the first supermassive black holes form and grow so quickly? What is the detailed history of cosmic Ryanization, and how did it affect subsequent galaxy evolution? Addressing these questions will require continued advancements in observational capabilities and theoretical modeling. Upcoming facilities promise to push our understanding even further. The Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSST, will provide a vast catalogue of high redshift galaxy candidates for follow-up study. Next-generation extremely large telescopes, such as the 30-meter telescope and the European Extremely Large Telescope, will enable detailed spectroscopic studies of early galaxies, probing their internal structures and chemical compositions. In the more distant future, proposed space-based observatories could potentially detect the very first luminous objects in the universe, perhaps even individual population 3 stars. In conclusion, the study of galaxies in the early universe stands at the frontier of modern astrophysics, challenging our understanding of fundamental physics and pushing the limits of observational technology. These ancient cosmic structures serve as laboratories for testing theories of galaxy formation, black hole growth, and cosmic evolution. As we continue to peer deeper into cosmic history, we not only unravel the mysteries of the universe's infancy, but also gain insights into the processes that ultimately led to the emergence of our own galaxy and the conditions necessary for life. The ongoing exploration of the early universe promises to yield new discoveries and insights, continually reshaping our understanding of cosmic origins and evolution. As we contemplate the earliest galaxies emerging from the cosmic dawn, our attention is naturally drawn to the larger structures into which these primordial systems are organized. The universe, far from being a homogeneous expanse, displays a rich tapestry of filaments, clusters, and voids on the largest scales. These cosmic structures, formed through the gravitational dance of dark matter and baryons, represent the culmination of billions of years of evolution. Let us now turn our gaze to these grand assemblies of galaxies, exploring how they form, evolve, and shape our understanding of the universe's architecture. Groups and clusters of galaxies represent the largest gravitationally bound structures in the universe, serving as cosmic laboratories for studying galaxy evolution, dark matter dynamics, and the properties of the intergalactic medium. These vast assemblies of galaxies, ranging from small groups of a few members to rich clusters containing thousands of galaxies, play a crucial role in shaping the large-scale structure of the cosmos and offer unique insights into fundamental physics and cosmology. The study of galaxy clusters has a rich history dating back to the 18th century, when Charles Messier and William Herschel first catalogued nebulous objects that we now recognize as nearby galaxy clusters. However, it wasn't until the early 20th century that the true nature and scale of these systems began to be understood. In the 1930s, Fritz Zwicky's study of the Coma cluster led to the first evidence for dark matter, as he observed that the cluster's galaxies were moving too fast to be held together by the visible mass alone. This missing mass problem in clusters foreshadowed the broader dark matter paradigm that now underpins our understanding of cosmic structure formation. Galaxy clusters are typically classified based on their richness, number of member galaxies, and morphology. The Abel catalogue, compiled by George Abel in 1958, remains a foundational resource in cluster studies, defining rich clusters as those with at least 50 galaxies within a specific magnitude range and radius. Clusters can be further categorized into regular, symmetric, relaxed, and irregular, asymmetric, often showing signs of recent mergers types. This classification reflects the dynamical state of the cluster and provides clues about its formation history. At the heart of most galaxy clusters lies a massive elliptical galaxy, often referred to as the brightest cluster galaxy, BCG. These giant galaxies, which can be up to 10 times more massive than the Milky Way, are thought to form through multiple mergers of smaller galaxies over cosmic time. The properties of BCGs, including their size, mass, and stellar populations, provide important constraints on models of galaxy formation and evolution in dense environments. The space between galaxies in clusters is filled with a hot, diffuse plasma known as the intra-cluster medium, ICM. With temperatures ranging from 10^7 to 10^8 Kelvin, this gas emits strongly in X-rays, making X-ray observations a powerful tool for studying cluster properties. The ICM, which contains most of the baryonic matter in clusters, plays a crucial role in cluster dynamics and galaxy evolution. Processes such as ram pressure stripping, where the ICM removes gas from infalling galaxies, can dramatically affect star formation and morphology in cluster galaxies. One of the most powerful applications of galaxy clusters in cosmology is their use as gravitational lenses. The enormous mass of clusters, dominated by dark matter, can bend and magnify light from more distant sources. This effect, predicted by Einstein's theory of general relativity, allows astronomers to study extremely distant and faint galaxies that would otherwise be unobservable. Notable examples include the Hubble Frontier Fields program, which used massive clusters as cosmic telescopes to probe the early universe. The study of galaxy clusters has been revolutionized by multi-wavelength observations. X-ray observatories like Chandra and XMM Newton have provided detailed maps of the hot ICM, revealing complex structures such as cold fronts and shock waves that trace the dynamical history of clusters. In the radio regime, observations have revealed diffuse synchrotron emission in the form of radio halos and relics, providing insights into particle acceleration processes and magnetic fields in the ICM. Optical and infrared surveys, such as the Sloan Digital Sky Survey, have dramatically increased the number of known clusters and enabled large statistical studies of cluster properties. The Sunyaev-Zeldovich (SZ) effect, a distortion of the cosmic microwave background radiation caused by scattering off hot electrons in the ICM, has emerged as a powerful tool for detecting and studying clusters. Unlike X-ray emission, the SZ effect is not subject to cosmological dimming, allowing for the detection of distant clusters that are difficult to observe by other means. Surveys using the SZ effect, such as those conducted by the South Pole Telescope and the Planck satellite, have discovered numerous high redshift clusters, pushing our understanding of cluster formation to earlier cosmic epochs. Galaxy clusters serve as important probes of cosmology and fundamental physics. The abundance and growth of massive clusters over cosmic time is highly sensitive to cosmological parameters, including the nature of dark energy. Observations of cluster abundances have provided independent constraints on these parameters, complementing other cosmological probes, such as the cosmic microwave background and type Ia supernovae. Additionally, studies of the gas fraction in relaxed clusters have been used to constrain the cosmic baryon fraction, providing a critical test of Big Bang nucleosynthesis predictions. Recent years have seen significant advancements in our understanding of the complex interplay between active galactic nuclei, AGN, and the ICM. X-ray observations have revealed cavities and bubbles in the ICM, interpreted as the result of AGN jet activity. This AGN feedback is now recognized as a crucial mechanism for regulating the cooling of gas in cluster cores, preventing runaway star formation in BCGs, and maintaining the observed properties of clusters over cosmic time. The dynamics of dark matter in clusters provides a unique laboratory for testing theories of modified gravity and the nature of dark matter itself. Observations of colliding clusters, such as the famous bullet cluster, have provided some of the strongest evidence for the existence of dark matter as a distinct component from ordinary baryonic matter. These systems, where the dark matter and gas components become spatially separated during the collision, offer a powerful way to test alternative theories of gravity that attempt to explain galaxy dynamics without invoking dark matter. Looking to the future, several key questions about galaxy groups and clusters remain to be answered. How do the first protoclusters form and evolve in the early universe? What is the detailed physics of AGN feedback and its role in cluster evolution? How can we reconcile tensions between cluster-based cosmological constraints and those from other probes? Addressing these questions will require continued advancements in observational capabilities and theoretical modeling. Upcoming missions and facilities promise to push our understanding even further. The Rosetta X-ray telescope, launched in 2019, is conducting an all-sky survey that will detect tens of thousands of galaxy clusters, providing an unprecedented sample for statistical studies. The Vera-C, Rubin Observatory's Legacy Survey of Space and Time, LSST, will discover and characterize numerous optical clusters, potentially revealing new classes of these systems. In the more distant future, proposed X-ray observatories like Athena will provide detailed views of the hot gas in distant clusters, offering new insights into cluster formation and evolution. In conclusion, galaxy groups and clusters stand as cosmic beacons, illuminating our understanding of structure formation, galaxy evolution, and fundamental physics. From their role as gravitational lenses probing the early universe to their use as cosmological probes, these massive systems continue to be at the forefront of astrophysical research. As we continue to study these grand assemblies of galaxies, we not only unravel the history of cosmic structure formation, but also gain insights into the fundamental laws that govern our universe. As we contemplate the vast cosmic structures of galaxy clusters, our attention is drawn to the intense bursts of star formation that can occur within individual galaxies. These starburst galaxies, characterized by their exceptionally high rates of star formation, represent some of the most extreme and energetic phenomena in the universe. Let us now turn our focus to these cosmic crucibles of stellar birth, exploring how they form, evolve, and impact our understanding of galaxy evolution and the cosmic history of star formation. Starburst galaxies and regions of intense star formation represent some of the most dynamic and energetic phenomena in the universe, serving as cosmic crucibles where new stars are born at prodigious rates. These extraordinary systems, characterized by star formation rates that can exceed hundreds or even thousands of solar masses per year, play a crucial role in shaping galactic evolution and enriching the intergalactic medium with heavy elements. The study of starburst galaxies provides unique insights into the processes that drive and regulate star formation, the interaction between stellar feedback and the interstellar medium, and the cosmic history of star formation and galaxy assembly. The concept of starburst galaxies emerged in the late 1970s and early 1980s as astronomers began to recognize a class of galaxies with unusually high rates of star formation compared to normal spiral galaxies. These systems were often associated with strong infrared emission, indicating the presence of large amounts of dust heated by young massive stars. The archetypal starburst galaxy M82, located in the nearby M81 group, became a prime target for multi-wavelength studies, revealing the complex interplay between star formation, galactic winds, and the surrounding interstellar and intergalactic media. At its core, a starburst is defined by a rate of star formation that cannot be sustained over the entire lifetime of a galaxy. Typical starburst episodes last for about 10 to 100 million years, during which a significant fraction of the galaxy's gas reservoir is converted into stars. This intense period of star formation can be triggered by various mechanisms, including galaxy mergers, tidal interactions, bar instabilities, or the infall of gas from the intergalactic medium. The exact definition of what constitutes a starburst can vary, but generally, it involves star formation rates at least several times higher than the long-term average for a galaxy of a given mass. One of the key characteristics of starburst galaxies is their high efficiency in converting gas into stars. While normal spiral galaxies like the Milky Way typically convert only a few % of their gas into stars each dynamical time, starburst galaxies can have star formation efficiencies an order of magnitude higher. This increased efficiency is often associated with high gas densities and turbulence, which promote the formation of massive molecular clouds and the subsequent collapse of these clouds into stars. The intense star formation in starburst galaxies has profound effects on their surrounding environment. The energy and momentum injected into the interstellar medium by stellar winds, supernovae, and radiation pressure from massive stars can drive powerful galactic outflows. These outflows, often observed as galactic winds, can expel significant amounts of gas and metals from the galaxy, enriching the intergalactic medium and potentially regulating future star formation. The famous superwind in M82, visible in optical, X-ray, and radio observations, serves as a prime example of this phenomenon. The study of starburst galaxies has been revolutionized by multi-wavelength observations. Infrared observations, particularly from space-based telescopes like Spitzer and Herschel, have been crucial in revealing the dust-enshrouded star formation that is often obscured at optical wavelengths. The far-infrared luminosity of galaxies has become a key indicator of their star formation rates, especially in highly dust-obscured systems. Radio observations, tracing both thermal emission from HII regions and non-thermal synchrotron emission from supernova remnants, provide complementary measures of recent star formation activity. In the local universe, luminous and ultraluminous infrared galaxies, LARGs and ULARGs, represent some of the most extreme examples of starburst activity. These systems, with infrared luminosities exceeding 10^11 and 10^12 solar luminosities respectively, are often associated with major galaxy mergers. The prototypical ULARG ARP220, for instance, is a late-stage merger with an estimated star formation rate of several hundred solar masses per year, concentrated in a highly obscured nuclear region. The connection between starburst activity and galaxy mergers has been a key area of research. Numerical simulations have shown that the gravitational torques induced during galaxy mergers can funnel large amounts of gas to the central regions of the merging system, triggering intense bursts of star formation. This scenario is supported by observations of enhanced star formation rates in interacting galaxy pairs and in post-merger systems. However, it's important to note that not all starbursts are triggered by mergers, and not all mergers result in starbursts, highlighting the complex nature of star formation regulation in galaxies. Recent years have seen increased focus on the role of starburst galaxies in the early universe. Observations with facilities like the Atacama Large Millimeter Submillimeter Array, ALMA, have revealed populations of dusty star-forming galaxies at high redshifts, some with star formation rates exceeding 1,000 solar masses per year. These systems, often identified through their bright sub-millimeter emission, may represent an important phase in the formation of massive elliptical galaxies observed in the local universe. The feedback processes associated with starburst activity play a crucial role in models of galaxy evolution. The energy and momentum injected into the interstellar medium by stellar winds and supernovae can heat and expel gas, potentially quenching further star formation. This negative feedback is thought to be an important mechanism for regulating galaxy growth and establishing the observed relationships between galaxy properties, such as the correlation between stellar mass and metallicity. However, the details of how this feedback operates and its effectiveness in different galactic environments remain active areas of research. The study of star formation in extreme environments has implications beyond galaxy evolution. The intense ultraviolet radiation and cosmic rays produced in starburst regions can drive complex astrochemistry, potentially producing prebiotic molecules. Additionally, the high rate of supernova explosions in starbursts makes them promising sites for the production of heavy elements and potential sources of high-energy cosmic rays and neutrinos. Looking to the future, several key questions about starburst galaxies and intense star formation remain to be answered. How do the most extreme starbursts in the early universe form and evolve? What determines the duration and efficiency of starburst episodes? How does the initial mass function of stars vary in these extreme environments? Addressing these questions will require continued advancements in observational capabilities and theoretical modeling. Upcoming missions and facilities promise to push our understanding even further. The James Webb Space Telescope is poised to provide unprecedented views of dust-obscured star formation in the early universe, potentially revealing the birth of the first galaxies. Next-generation radio telescopes like the Square Kilometre Array will map the neutral hydrogen content of galaxies over cosmic time, providing new insights into the fuel for star formation. In the more distant future, gravitational wave observatories may detect the mergers of massive stars in starburst galaxies, offering a new probe of star formation in extreme environments. In conclusion, starburst galaxies and regions of intense star formation represent cosmic laboratories where the processes of stellar birth and galactic evolution are pushed to their extremes, from their role in enriching the intergalactic medium to their potential as factories for prebiotic molecules. These systems continue to challenge and expand our understanding of the universe. As we continue to study these cosmic crucibles of star formation, we not only unravel the history of galaxy assembly, but also gain insights into the fundamental processes that have shaped the visible universe over cosmic time. As we contemplate the furious stellar nurseries of starburst galaxies, our gaze naturally turns to the diverse stellar populations that result from these and other star formation episodes throughout cosmic history. The study of stellar populations in galaxies provides a crucial link between the microscopic processes of stellar evolution and the macroscopic properties of galaxies. Let us now explore how the analysis of stellar populations serves as a cosmic archaeological tool, revealing the star formation and chemical enrichment history of galaxies across the universe. Stellar populations in galaxies represent the fundamental building blocks of cosmic structure, serving as living fossils that encode the history of star formation, chemical enrichment, and dynamical evolution of their host systems. The study of these diverse assemblages of stars provides crucial insights into the processes that have shaped galaxies over cosmic time, from the formation of the first stars in the early universe to the complex ecosystems of modern galaxies. By analyzing the ages, compositions, and distributions of stellar populations, astronomers can unravel the cosmic history of galaxies and probe the physical mechanisms that drive galactic evolution. The concept of stellar populations has its roots in the pioneering work of Walter Baade in the 1940s. Baade's observations of the Andromeda Galaxy, M31, and its satellites led to the recognition of two distinct stellar populations. Population 1, consisting of young, metal-rich stars found in the disk of spiral galaxies, and Population 2, comprising older, metal-poor stars in globular clusters and galactic halos. This fundamental dichotomy laid the groundwork for our understanding of galactic structure and evolution, revealing that galaxies are not homogeneous entities, but rather complex systems with distinct components and histories. As our understanding of stellar evolution and galactic structure has advanced, the classification of stellar populations has become more nuanced. Modern studies recognize a continuum of populations, from the extremely metal-poor stars formed in the early universe to the metal-rich stars born in recent epochs. In the Milky Way, for instance, astronomers distinguish between thin disk, thick disk, and halo populations, each with distinct kinematic and chemical properties that reflect different formation histories and evolutionary paths. The study of stellar populations in elliptical galaxies has been particularly revealing. These systems, once thought to be simple, homogeneous collections of old stars, have been shown to possess complex star formation histories. Detailed spectroscopic studies have revealed evidence of multiple episodes of star formation, challenging the traditional view of ellipticals as products of a single, ancient burst of star formation. The presence of gradients in age and metallicity within these galaxies provides clues to their assembly history, potentially including major mergers and accretion events. In spiral galaxies, the distribution of stellar populations reflects the ongoing process of disk formation and evolution. The disk typically shows a gradient in both age and metallicity, with older, more metal-poor stars dominating at larger radii. This pattern is generally interpreted as evidence for inside-out disk formation, where star formation proceeds more rapidly in the inner regions of the galaxy. However, recent studies have revealed complexities in this picture, including the effects of radial migration, where stars can move to different parts of the disk over time, blurring the simple relationship between a star's current location and its birth site. One of the most powerful tools for studying stellar populations is the color magnitude diagram, CMD, which plots the brightness of stars against their color, a proxy for temperature. The morphology of features in the CMD, such as the main sequence turnoff, the red giant branch, and the horizontal branch, provides direct information about the age and metallicity of a stellar population. The advent of space-based observatories like the Hubble Space Telescope has allowed for the creation of exquisitely detailed CMDs for nearby galaxies, revealing their star formation histories with unprecedented precision. The initial mass function, IMF, which describes the distribution of stellar masses at birth, is a crucial aspect of stellar population studies. The IMF affects the integrated properties of galaxies, including their mass-to-light ratios and chemical evolution. While the IMF was long thought to be universal, recent evidence suggests that it may vary in different environments. Studies of massive elliptical galaxies, for instance, have indicated a potential excess of low-mass stars compared to the Milky Way IMF, with significant implications for our understanding of galaxy formation and evolution. Advances in spectroscopic techniques have revolutionized the study of stellar populations in distant galaxies. The development of integral field spectroscopy, which provides spatially resolved spectra across an entire galaxy, has allowed for detailed mapping of stellar population properties. Surveys like CALIPHA, MANGA, and SAMI have applied this technique to large samples of galaxies, revealing the spatial variations in age, metallicity, and star formation history across different galaxy types and environments. The chemical composition of stellar populations provides a crucial link to the history of nucleosynthesis and chemical enrichment in galaxies. The abundance patterns of various elements, from the A elements produced primarily in core collapse supernovae to the iron peak elements synthesized in type Ia supernovae, offer insights into the timescales and processes of star formation. For example, the enhanced A-element abundances observed in elliptical galaxies suggest a rapid early phase of star formation, while the more extended star formation histories of spiral galaxies are reflected in their more solar-like abundance patterns. The study of stellar populations extends beyond the local universe. Observations of high redshift galaxies provide snapshots of stellar populations at earlier cosmic epochs, allowing astronomers to directly trace the evolution of galaxies over time. Techniques such as spectral energy distribution fitting and spectroscopic analysis of integrated light have been applied to galaxies at redshifts greater than 2, revealing the buildup of stellar mass and the evolution of star formation rates across cosmic history. Recent years have seen increased focus on the low-mass, low-surface brightness regime of the stellar population distribution. Ultra-faint dwarf galaxies, some with total luminosities less than individual bright stars, have been discovered in the local group. These systems, with their extremely metal-poor stellar populations, may represent some of the earliest formed galaxies and provide a window into star formation in the early universe. The connection between stellar populations and the interstellar medium ISM is a key area of ongoing research. The chemical composition of young stars reflects the current state of the ISM from which they formed, while older populations provide a record of past enrichment. Studies of the relationship between stellar metallicity and gas phase metallicity in galaxies offer insights into the processes of gas inflow, outflow, and recycling that drive galactic chemical evolution. Looking to the future, several key questions about stellar populations in galaxies remain to be answered. How do the properties of stellar populations vary across the full spectrum of galaxy types and environments? What is the detailed star formation and chemical enrichment history of the Milky Way and nearby galaxies? How universal is the initial mass function, and how does it vary with environment and cosmic time? Addressing these questions will require continued advancements in observational capabilities and theoretical modeling. Upcoming missions and facilities promise to push our understanding even further. The James Webb Space Telescope will provide unprecedented views of stellar populations in distant galaxies, potentially revealing the properties of the first generations of stars. The Vera C. Rubin Observatory's Legacy Survey of Space and Time will discover and characterize billions of stars in the Milky Way and nearby galaxies, offering a comprehensive view of stellar populations in the local universe. In the more distant future, extremely large telescopes will enable detailed spectroscopic studies of individual stars in galaxies beyond the local group. In conclusion, the study of stellar populations in galaxies stands as a cornerstone of modern astrophysics, providing a cosmic archaeological record that connects the lives of individual stars to the grand narrative of galactic evolution. From the metal-poor relics of the early universe to the ongoing star formation in galactic disks, these stellar assemblages encode the history of galaxy formation and evolution. As we continue to unravel the complexities of stellar populations, we not only deepen our understanding of galactic processes, but also gain insights into the fundamental mechanisms that have shaped the visible universe over cosmic time. As we reflect on the diverse stellar populations that compose galaxies, our attention is drawn to the vast, diffuse regions that surround these cosmic islands of stars. The galactic halo, a sphere of stars, globular clusters, and dark matter extending far beyond the visible disk, holds key clues to the formation and evolution of galaxies. Let us now turn our gaze outward to explore these galactic outskirts and the substructures that inhabit them, unraveling the story of galactic assembly written in the stars of the halo. Galactic halos and substructures represent some of the most intriguing and revealing components of galaxies, offering crucial insights into the processes of galaxy formation and evolution. These vast, diffuse regions extending far beyond the visible disks of galaxies serve as cosmic archaeological sites, preserving the remnants of past merger events and providing a window into the hierarchical assembly of galaxies over cosmic time. The study of galactic halos and their substructures has revolutionized our understanding of galaxy evolution, dark matter distribution, and the connection between galaxies and the larger cosmic web. The concept of galactic halos dates back to the mid-20th century, with the recognition that the Milky Way is surrounded by a population of old, metal-poor stars and globular clusters extending far beyond the disk. However, it wasn't until the advent of large-scale digital sky surveys and deep imaging techniques that the true complexity and richness of galactic halos began to be revealed. The Sloan Digital Sky Survey, SDSS in particular, has been instrumental in mapping the structure of the Milky Way's halo and discovering numerous substructures within it. Galactic halos are typically characterized by their vast extent, low stellar densities, and predominantly old, metal-poor stellar populations. In the case of the Milky Way, the stellar halo extends to at least 100 kiloparsecs from the galactic center, with a total mass of about 1% of the galaxy's stellar mass. This diffuse component is thought to be primarily composed of stars accreted from smaller galaxies over the course of the Milky Way's assembly history. The chemical and kinematic properties of halo stars provide crucial information about the nature and timing of these accretion events. One of the most significant discoveries in recent years has been the ubiquity of substructures within galactic halos. These substructures, which include stellar streams, shells, and overdensities, are the remnants of past and ongoing accretion events. The most prominent example in the Milky Way is the Sagittarius stream, a long ribbon of stars wrapping around the galaxy multiple times, originating from the ongoing disruption of the Sagittarius dwarf spheroidal galaxy. Other notable structures include the Monoceros ring, the Orphan stream, and the Virgo overdensity, each telling a unique story of galactic cannibalism. The discovery and characterization of these halo substructures have been greatly facilitated by astrometric missions like Gaia. Launched in 2013, Gaia has provided unprecedented measurements of the positions, distances, and proper motions of over 1 billion stars in the Milky Way. This wealth of data has allowed astronomers to identify new stellar streams, trace their orbits, and reconstruct the accretion history of the galaxy with remarkable detail. For instance, Gaia data has revealed that much of the Milky Way's inner halo was formed by a single, massive accretion event dubbed Gaia Enceladus, or the Gaia sausage, which occurred approximately 10 billion years ago. The distribution of stars and substructures in galactic halos provides crucial constraints on models of galaxy formation and evolution. In the current paradigm of hierarchical structure formation, galaxies grow through the accretion of smaller systems. The properties of halo substructures, such as their spatial distribution, kinematics, and chemical compositions, offer a direct test of this model. Moreover, the degree of phase mixing and relaxation in these structures provides information about the dynamical history of the host galaxy and the properties of its gravitational potential. Beyond the stellar component, galactic halos are dominated by dark matter. Cosmological simulations predict that dark matter halos should contain numerous subhalos, remnants of the hierarchical formation process. While the most massive of these subhalos may host luminous satellite galaxies, the vast majority are expected to be too small to retain gas and form stars, remaining as dark substructures. The search for these dark subhalos and their potential effects on visible halo structures is an active area of research, with implications for our understanding of dark matter physics. The study of galactic halos extends beyond the Milky Way. Deep imaging of nearby galaxies, particularly with the Hubble Space Telescope, has revealed faint stellar halos around many systems. These observations have shown that halo properties, such as their extent and the presence of substructures, vary significantly among galaxies of different masses and morphologies. For instance, massive elliptical galaxies often show evidence of multiple accretion events in their extended halos, reflecting their complex assembly histories. One of the most challenging aspects of studying galactic halos is their extremely low surface brightness. The outer regions of galactic halos typically have surface brightnesses fainter than 30 magnitudes per square arc second, pushing the limits of even the most sensitive detectors. Innovative techniques, such as stacking images of multiple galaxies or using novel low surface brightness imaging methods, have been developed to overcome these challenges. Future facilities like the Vera C. Rubin Observatory promise to push these limits even further, potentially revealing the full extent of galactic halos and their faintest substructures. The connection between galactic halos and the intergalactic medium, IGM, is an area of growing interest. The outermost regions of galactic halos are thought to transition into the cosmic web of filaments and voids that make up the large-scale structure of the universe. This transition region, sometimes referred to as the circumgalactic medium, CGM, plays a crucial role in galaxy evolution by mediating the flow of gas into and out of galaxies. Studies of the CGM through absorption line spectroscopy of background quasars have revealed complex gas dynamics and chemical enrichment patterns, providing insights into the baryon cycle that regulates galaxy growth. Recent years have seen increased focus on the role of galactic halos in the missing baryon problem. Observations suggest that a significant fraction of the baryons predicted by cosmic abundance measurements are not accounted for in the visible components of galaxies and the intergalactic medium. Theoretical models and some observational evidence suggest that a substantial portion of these missing baryons may reside in a hot, diffuse phase in galactic halos. Detecting and characterizing this hot halo gas remains a major observational challenge, with potential implications for our understanding of galaxy formation and cosmology. The study of stellar populations in galactic halos provides a unique window into the early epochs of galaxy formation. The most metal-poor stars in the halo are thought to be among the oldest in the universe, potentially preserving the chemical signatures of the first generations of stars. Detailed spectroscopic studies of these ancient stars offer insights into the nucleosynthesis processes in the early universe and the chemical enrichment history of galaxies. Looking to the future, several key questions about galactic halos and substructures remain to be answered. What is the full extent of galactic halos, and how do they connect to the cosmic web? How do the properties of galactic halos vary across the full spectrum of galaxy masses and environments? What is the nature of the smallest dark matter subhalos, and can they be detected through their gravitational effects? Addressing these questions will require continued advancements in observational capabilities and theoretical modeling. Upcoming missions and facilities promise to push our understanding even further. The James Webb Space Telescope will provide unprecedented views of the stellar populations in nearby galactic halos, potentially revealing their assembly histories with new clarity. The Vera C. Rubin Observatory's legacy survey of space and time will map the Milky Way's halo to unprecedented depths, likely discovering numerous new substructures and stellar streams. In the more distant future, proposed X-ray missions could potentially detect the hot gas in galactic halos, providing a complete picture of their baryonic content. In conclusion, the study of galactic halos and substructures stands at the forefront of modern astrophysics, offering a unique perspective on the processes of galaxy formation and evolution. From the stellar fossils of ancient accretion events to the ongoing disruption of satellite galaxies, these outer realms of galaxies preserve a rich record of cosmic history. As we continue to explore these diffuse yet revealing components of galaxies, we not only unravel the assembly histories of individual systems, but also gain crucial insights into the fundamental processes that have shaped the universe over billions of years. As we contemplate the vast, diffuse halos that envelop galaxies, our attention is drawn to another cosmic force that permeates these systems: magnetism. The magnetic fields threading through galaxies, though often overlooked, play a crucial role in shaping the evolution and structure of these cosmic islands. Let us now turn our focus to the intricate dance of charged particles and magnetic fields that influences everything from star formation to the propagation of cosmic rays throughout galactic systems. Magnetism in galaxies represents a pervasive and influential force that shapes the structure, dynamics, and evolution of these vast cosmic systems. Though often overshadowed by gravity in discussions of galactic physics, magnetic fields play a crucial role in various astrophysical processes, from star formation to the propagation of cosmic rays and the generation of large-scale galactic structures. The study of galactic magnetism offers unique insights into the complex interplay between gas dynamics, stellar feedback, and the intergalactic medium, providing a more complete picture of galaxy evolution and the cosmic web. The exploration of galactic magnetic fields dates back to the mid-20th century, with the pioneering work of Hannes Alfvén, who proposed the concept of magnetohydrodynamics, MHD, to describe the behavior of conducting fluids in the presence of magnetic fields. However, it wasn't until the development of radio astronomy that direct observations of galactic magnetic fields became possible. The detection of polarized synchrotron emission from cosmic ray electrons spiraling around magnetic field lines provided the first concrete evidence for large-scale magnetic fields in external galaxies. Galactic magnetic fields typically have strengths on the order of a few microgauss (mg) in the interstellar medium, with variations depending on the environment. In dense molecular clouds, field strengths can reach hundreds of microgauss, while in the diffuse halo, they may be as weak as a fraction of a microgauss. Despite these seemingly small values, the vast scales over which these fields operate make them a significant factor in galactic dynamics. The energy density of the magnetic field is often comparable to that of turbulent gas motions and cosmic rays, suggesting a state of rough equipartition between these components in many galaxies. The origin and amplification of galactic magnetic fields remain subjects of active research and debate. The prevailing theory involves a combination of processes, starting with a weak seed field that is amplified over time. This seed field could originate from primordial magnetic fields generated in the early universe, or from small-scale dynamos operating in the first stars and galaxies. Once established, these fields are thought to be amplified and maintained by galactic dynamo mechanisms, which convert kinetic energy from galactic rotation and turbulence into magnetic energy. One of the most powerful tools for studying galactic magnetism is the observation of Faraday rotation. This effect occurs when polarized radio waves pass through a magnetized plasma, causing a rotation of the plane of polarization proportional to the magnetic field strength along the line of sight. By measuring this rotation at different radio frequencies, astronomers can construct detailed maps of the magnetic field structure in galaxies. Large-scale surveys, such as the NRAO VLA Sky Survey (NVSS), have provided Faraday rotation measurements for thousands of extragalactic radio sources, allowing for studies of magnetic fields on cosmic scales. The structure of galactic magnetic fields often mirrors the large-scale structure of the galaxies themselves. In spiral galaxies, the magnetic field typically follows the spiral arms, with a significant ordered component aligned with the disk. This ordered field is thought to be generated and maintained by the AO dynamo, where differential rotation, the O effect, stretches field lines, and helical turbulence, the A effect, lifts and twists them. In addition to this ordered component, there is also a significant turbulent component, particularly in regions of active star formation. The role of magnetic fields in star formation is an area of intense study. While gravity is the primary driver of molecular cloud collapse, magnetic fields can provide support against gravitational contraction, potentially regulating the star formation process. The relative importance of magnetic support versus turbulence in determining star formation rates and efficiencies is a topic of ongoing debate. Observations of magnetic fields in molecular clouds, through techniques such as dust polarization measurements, are providing new insights into this complex interplay. Galactic magnetic fields also play a crucial role in the propagation and confinement of cosmic rays. These high-energy particles, primarily protons and atomic nuclei, spiral around magnetic field lines, their paths determined by the strength and configuration of the field. The confinement of cosmic rays by galactic magnetic fields is essential for understanding their origin, energy spectrum, and the cosmic ray energy density in galaxies. Moreover, the interaction between cosmic rays and magnetic fields can drive galactic winds and influence the structure of the interstellar medium. Recent years have seen significant advancements in our ability to observe and model galactic magnetic fields. The development of wideband radio receivers and advanced data processing techniques has allowed for more precise and extensive Faraday rotation measurements. Polarization observations at multiple wavelengths, from radio to optical, are providing a more complete picture of magnetic field structures across different galactic environments. In the millimeter and sub-millimeter regime, facilities like ALMA, Atacama Large Millimeter Submillimeter Array, are revealing magnetic fields in the dense regions where stars form. The study of magnetic fields in different types of galaxies has revealed intriguing variations. While spiral galaxies typically show well-ordered fields aligned with their disks, Elliptical galaxies often exhibit more complex, seemingly random field configurations. In some cases, particularly in galaxy clusters, large-scale magnetic fields have been detected in the intergalactic medium, suggesting that magnetism plays a role in the largest structures in the universe. The connection between galactic magnetic fields and large-scale structure formation is an emerging area of research. Observations and simulations suggest that magnetic fields may influence the flow of gas along cosmic web filaments and into galaxies. Conversely, galactic outflows and AGN jets can magnetize the intergalactic medium, potentially affecting the evolution of the cosmic web. Understanding these processes requires a multi-scale approach, linking the physics of galaxy formation to the largest structures in the universe. One of the most exciting developments in the study of galactic magnetism is the potential for detecting primordial magnetic fields. These fields, potentially generated in the early universe, could have played a role in the formation of the first structures. While direct detection remains challenging, indirect methods, such as studying the magnetic fields in very high redshift galaxies or searching for specific signatures in the cosmic microwave background, offer promising avenues for constraining the strength and properties of primordial fields. Looking to the future, several key questions about magnetism in galaxies remain to be answered. How do magnetic fields influence the multiphase structure of the interstellar medium? What is the exact role of magnetic fields in regulating star formation on galactic scales? How do galactic magnetic fields connect to and interact with fields in the intergalactic medium? Addressing these questions will require continued advancements in observational capabilities and theoretical modeling. Upcoming facilities promise to revolutionize our understanding of galactic magnetism. The Square Kilometre Array, SKA, with its unprecedented sensitivity and survey speed, will map magnetic fields in millions of galaxies across cosmic time. This will allow for statistical studies of the evolution of galactic magnetism and its connection to other galactic properties. In space, missions like Millimetron could provide high-resolution polarization measurements of star-forming regions, revealing the role of magnetic fields in the earliest stages of star and planet formation. In conclusion, the study of magnetism in galaxies represents a crucial frontier in our quest to understand the complex ecosystems of these cosmic islands. From their role in star formation to their influence on large-scale structure, magnetic fields are integral to the physics of galaxies. As we continue to unravel the mysteries of galactic magnetism, we not only deepen our understanding of galaxy evolution, but also gain insights into fundamental processes that have shaped the universe from its earliest moments to the present day. As we contemplate the intricate magnetic fields threading through galaxies, our gaze is drawn to a class of galaxies that challenge our conventional understanding of these cosmic systems. Low-surface brightness galaxies, with their diffuse stellar distributions and enigmatic properties, offer a unique window into galaxy formation and evolution. Let us now turn our attention to these elusive objects, exploring how their study is reshaping our comprehension of galactic diversity and the role of dark matter in the universe. Low-surface brightness, LSB galaxies, represent a fascinating and enigmatic class of cosmic objects that challenge our understanding of galaxy formation and evolution. These elusive systems, characterized by their diffuse stellar distributions and faint overall luminosities, have emerged as crucial probes of dark matter dynamics and galactic structure. Despite their prevalence in the universe, LSB galaxies have long evaded detection due to observational biases, making them a relatively recent addition to the pantheon of known galactic types. The study of LSB galaxies traces its origins to the 1970s and 1980s, with pioneering work by astronomers like Vera Rubin and Steve McGaw. However, it wasn't until the advent of more sensitive detectors and specialized observing techniques that the true abundance and diversity of these systems began to be revealed. LSB galaxies are typically defined as having central surface brightnesses fainter than 22 magnitudes per square arc-second in the B-band, significantly dimmer than the night sky as seen from Earth. This low surface brightness makes them challenging to detect against the sky background, leading to their underrepresentation in traditional galaxy surveys. The physical properties of LSB galaxies often defy expectations based on observations of their higher surface brightness counterparts. Many LSB galaxies are rich in neutral hydrogen gas but show relatively low star formation rates, suggesting inefficient conversion of gas into stars. Their stellar populations tend to be dominated by old Chablis low metallicity stars, indicating a history of slow, sporadic star formation. Morphologically, LSB galaxies span a range of types, from diffuse irregulars to spiral systems with low contrast arms, challenging our understanding of the mechanisms that drive galactic structure formation. One of the most intriguing aspects of LSB galaxies is their apparent dark matter dominance. Rotation curve measurements of these systems often show that they are embedded in massive dark matter halos with mass-to-light ratios that can exceed 100 in solar units. This extreme dark matter dominance makes LSB galaxies ideal laboratories for testing theories of dark matter and modified gravity. The cuspy halo problem, where observed dark matter distributions in LSB galaxies appear less centrally concentrated than predicted by cold dark matter simulations, has been a particular focus of study and debate. The detection and characterization of LSB galaxies pose significant observational challenges. Traditional detection methods, optimized for high surface brightness objects, often fail to identify these diffuse systems. Innovative techniques, such as drift scanning and specialized image processing algorithms, have been developed to push the limits of low surface brightness detection. Space-based observatories, like the Hubble Space Telescope, have played a crucial role in revealing the detailed structure of nearby LSB galaxies, while wide-field surveys like the Sloan Digital Sky Survey have provided large statistical samples for study. Recent years have seen a surge of interest in a particular class of LSB galaxies known as ultra-diffuse galaxies, UDGs. These enigmatic objects have the sizes of large spiral galaxies, but the luminosities of small dwarfs, resulting in extremely low surface brightnesses. The discovery of large populations of UDGs in galaxy clusters, such as the Coma cluster, has raised intriguing questions about their formation and evolution. Some UDGs appear to be surprisingly deficient in dark matter, challenging our understanding of galaxy formation in a dark matter-dominated universe. The study of LSB galaxies extends beyond the optical regime. Radio observations, particularly of the 21 Cm line of neutral hydrogen, have been crucial in revealing the gas content and dynamics of these systems. Facilities like the Very Large Array and the Arecibo Observatory have mapped the extended HI disks of many LSB galaxies, often showing that the gas extends well beyond the visible stellar component. These observations provide crucial information about the total mass distribution and potential well of LSB galaxies. The origin and evolution of LSB galaxies remain subjects of active research and debate. Several formation scenarios have been proposed, including the possibility that they represent failed normal galaxies that experienced early quenching of star formation. Another hypothesis suggests that LSB galaxies form in low-density environments with reduced tidal interactions, allowing for the preservation of extended low-density structures. The role of feedback processes, both from supernovae and potential active galactic nuclei, in shaping the evolution of LSB galaxies is an area of ongoing investigation. The connection between LSB galaxies and the larger cosmic web is an emerging area of study. Observations suggest that many LSB galaxies reside in relatively isolated environments, often found in cosmic voids or on the outskirts of galaxy groups. This environmental preference may play a crucial role in their formation and evolution, potentially explaining their unusual properties. Understanding the distribution of LSB galaxies in the context of large-scale structure provides important constraints on models of galaxy formation and cosmic evolution. One of the most significant implications of LSB galaxy research is its impact on our understanding of the galaxy luminosity function and the cosmic baryon budget. The detection of large populations of previously unrecognized LSB galaxies suggests that current estimates of the total number and mass of galaxies in the universe may be incomplete. This has important consequences for our understanding of structure formation, the distribution of dark matter, and the overall matter content of the universe. Recent technological advancements have opened new avenues for LSB galaxy research. The development of large, low-noise CCDs and specialized optical designs has enabled the construction of telescopes optimized for low-surface brightness observations, such as the Dragonfly telephoto array. These instruments are pushing the boundaries of low-surface brightness astronomy, potentially revealing entire populations of previously undetected galaxies. Looking to the future, several key questions about LSB galaxies remain to be answered. What is the full extent of the LSB galaxy population, and how does it evolve over cosmic time? How do the unusual properties of LSB galaxies inform our understanding of galaxy formation and evolution? Can the dark matter distributions in LSB galaxies be reconciled with current cosmological models? Addressing these questions will require continued advancements in observational capabilities and theoretical modeling. Upcoming facilities promise to revolutionize our understanding of LSB galaxies. The Vera-C Rubin Observatory's Legacy Survey of Space and Time, LSST, will provide unprecedented deep, wide-field imaging that could reveal vast numbers of LSB galaxies across the sky. In the radio regime, the Square Kilometre Array, SKA, will map the neutral hydrogen content of LSB galaxies with extraordinary sensitivity, potentially detecting these systems out to cosmological distances. These observations will allow for statistical studies of LSB galaxy properties and their evolution over cosmic time. In conclusion, the study of low-surface brightness galaxies represents a crucial frontier in our quest to understand the full diversity of galactic systems in the universe, from their role as dark matter laboratories to their implications for galaxy formation theory. LSB galaxies continue to challenge and expand our cosmic perspective. As we push the boundaries of observation and theory, these faint yet revealing systems promise to shed light on some of the most fundamental questions in astrophysics and cosmology. As we contemplate the diffuse, enigmatic nature of low-surface brightness galaxies, our attention is drawn to another intriguing phenomenon in the galactic realm: the existence of dual nuclei in some galaxies. These systems, harboring two distinct galactic centers, offer a unique window into the processes of galaxy mergers and the growth of supermassive black holes. Let us now turn our focus to these cosmic duos, exploring how their study illuminates the dynamic nature of galactic evolution and the formation of some of the most massive objects in the universe. Galactic nuclei harboring dual supermassive black holes represent a fascinating and crucial stage in the evolution of galaxies, offering unique insights into the processes of galaxy mergers, the growth of supermassive black holes, and the dynamics of some of the most extreme gravitational environments in the universe. These systems, characterized by the presence of two distinct galactic centers within a single galaxy, serve as cosmic laboratories for studying the final stages of galaxy mergers and the prelude to supermassive black hole coalescence. The concept of dual galactic nuclei emerged from our understanding of galaxy evolution in a hierarchical universe. As galaxies grow through mergers and accretion, their central supermassive black holes are brought together by dynamical friction, eventually forming a bound pair. This process, while theoretically well established, has proven challenging to observe due to the vast distances between galaxies and the relatively short timescales of the final merger stages on cosmic scales. The search for dual active galactic nuclei, AGN, began in earnest in the late 20th century, with early candidates identified through double-peaked emission lines in optical spectra. However, it wasn't until the advent of high-resolution imaging and multi-wavelength observations that unambiguous detections became possible. One of the most famous early examples is NGC 6240, a nearby ultra-luminous infrared galaxy found to harbor two active nuclei separated by about 1 kiloparsec. This discovery, made using X-ray observations from the Chandra X-ray Observatory, provided compelling evidence for the existence of dual supermassive black holes in merging galaxies. The physical processes governing the evolution of dual supermassive black holes are complex and span a wide range of scales. As galaxies merge, Their central black holes sink towards the center of the newly formed system through dynamical friction against the stellar background. This process can take hundreds of millions of years for typical galaxy masses. Once the black holes reach a separation of about a parsec, they form a bound binary system. The final parsec problem, which refers to the challenge of bringing the black holes close enough to merge through gravitational wave emission, remains an active area of research in theoretical astrophysics. Observationally, dual AGN can manifest in various ways depending on their separation and activity levels. At larger separations, kiloparsec scales, they may appear as two distinct galactic bulges within a single, often disturbed in galaxy. Closer pairs, parsec scales, may be resolved only through very long baseline interferometry, VLBI, in the radio regime. In some cases, the presence of dual AGN is inferred from periodic variations in the light curve of a single apparent source, suggesting orbital motion of two black holes. The study of dual galactic nuclei has been revolutionized by multi-wavelength observations. X-ray observations are particularly powerful for identifying accreting black holes, as the high energy emission can penetrate the dust and gas that often obscure galactic centers in optical light. Radio observations, especially using VLBI techniques, offer the highest spatial resolution capable of resolving parsec-scale separations in nearby galaxies. In the optical and infrared, adaptive optics systems on large ground-based telescopes have enabled high-resolution imaging of galactic cores, revealing double nuclei in several nearby galaxies. One of the most significant recent advancements in the field has been the development of large-scale surveys capable of identifying dual AGN candidates. The Sloan Digital Sky Survey, for instance, has been used to search for galaxies with double-peaked emission lines, a potential signature of two active nuclei with distinct velocities. Follow-up observations of these candidates with high-resolution imaging and spectroscopy have led to the confirmation of numerous dual AGN systems. The importance of dual galactic nuclei extends beyond their role as curiosities in galaxy evolution. These systems serve as crucial test beds for theories of black hole growth and AGN triggering in galaxy mergers. The relative activity levels of the two nuclei can provide insights into how gas is funneled to galactic centers during mergers and how this process relates to star formation and AGN activity. Moreover, the frequency and properties of dual AGN offer constraints on models of galaxy evolution and the merger rates of galaxies over cosmic time. The final stages of supermassive black hole mergers are of particular interest in the era of gravitational wave astronomy. While current gravitational wave detectors are not sensitive to the low frequencies produced by supermassive black hole mergers, future space-based detectors like LISA, Laser Interferometer Space Antenna, promise to open a new window on these events. The detection of gravitational waves from merging supermassive black holes would provide unprecedented insights into general relativity in the strong field regime and potentially reveal the detailed physics of black hole coalescence. The study of dual galactic nuclei also has implications for our understanding of AGN feedback and its role in galaxy evolution. As two AGN approach each other, their combined feedback effects could have profound impacts on the surrounding gas, potentially quenching star formation or driving powerful outflows. Understanding these processes is crucial for developing a complete picture of how galaxies evolve and how the growth of supermassive black holes is connected to the properties of their host galaxies. Recent years have seen increased focus on the possibility of offset AGN, where one supermassive black hole has been ejected from the galactic center due to gravitational wave recoil following a merger. These systems, while even more challenging to detect than dual AGN, could provide important constraints on the merger histories of galaxies and the properties of gravitational wave emission from black hole mergers. Looking to the future, several key questions about dual galactic nuclei remain to be answered. What is the true frequency of dual AGN in the universe, and how does this frequency evolve with cosmic time? How do dual AGN influence the evolution of their host galaxies, particularly in terms of star formation and morphological transformation? Can we develop more effective methods for identifying dual AGN candidates in large-scale surveys? Addressing these questions will require continued advancements in observational capabilities and theoretical modeling. Upcoming facilities promise to revolutionize our understanding of dual galactic nuclei. The James Webb Space Telescope, with its unprecedented infrared sensitivity and spatial resolution, will be able to peer through the dust in galactic centers, potentially revealing hidden dual AGN in nearby galaxies. In the radio regime, next-generation VLBI arrays will push the boundaries of spatial resolution, potentially resolving the orbits of the closest supermassive black hole binaries. The Vera C. Rubin Observatory's legacy survey of space and time will provide a vast dataset for identifying dual AGN candidates through both imaging and time domain studies. In conclusion, the study of dual galactic nuclei stands at the intersection of multiple fields in astrophysics, connecting the physics of supermassive black holes to the evolution of galaxies and the structure of the universe itself. These cosmic duos offer a unique window into some of the most extreme and dynamic processes in the universe, from the violent mergers of galaxies to the final death spiral of supermassive black holes. As we continue to unravel their mysteries, we not only learn about these fascinating systems, but also gain crucial insights into the fundamental processes that have shaped the cosmos over billions of years. As we contemplate the dynamic dance of dual galactic nuclei, our gaze is drawn to another class of galaxies that challenge our understanding of galactic structure and evolution. Ultra-diffuse galaxies, with their enigmatically large sizes but low stellar densities, represent a cosmic puzzle that is reshaping our views on galaxy formation and the nature of dark matter. Let us now turn our attention to these ghostly giants of the cosmos, exploring how their study is opening new frontiers in astrophysics and cosmology. Ultra-diffuse galaxies, UDGs, represent one of the most enigmatic and intriguing classes of astronomical objects discovered in recent years. These ghostly giants of the cosmos challenge our understanding of galaxy formation and evolution, pushing the boundaries of what we thought possible in terms of galactic structure and composition. Characterized by their extremely low surface brightness and unexpectedly large sizes, UDGs have emerged as a crucial testing ground for theories of dark matter, galaxy evolution, and the physics of the early universe. The story of UDGs began in earnest in 2015, when a team led by Peter Van Dokkum of Yale University reported the discovery of a substantial population of these galaxies in the Coma cluster. Using the Dragonfly telephoto array, a telescope specifically designed for low-surface brightness astronomy, they identified 47 galaxies with sizes comparable to the Milky Way, but containing only about 1% of its stars. This discovery sparked a flurry of research activity, as astronomers realized that these objects might represent an entirely new class of galaxies that had previously escaped detection due to their faint nature. Ultra-diffuse galaxies are defined by their extremely low surface brightness, typically less than 24 magnitudes per square arc-second in the G-band, and their large effective radii, often exceeding 1.5 kiloparsecs. To put this in perspective, UDGs can have sizes similar to large spiral galaxies like the Milky Way, but contain only a tiny fraction of the stars, resulting in a diffuse, ghostly appearance. This unusual combination of properties raises fundamental questions about their formation, evolution, and the role of dark matter in shaping their structure. The detection and characterization of UDGs pose significant observational challenges. Their low surface brightness makes them difficult to detect against the sky background, requiring specialized instruments and observing techniques. The Dragonfly telephoto array, with its innovative design using commercial camera lenses to minimize scattered light, has been particularly effective in identifying these elusive objects. Follow-up observations using large ground-based telescopes and space-based observatories like the Hubble Space Telescope have been crucial in revealing the detailed properties of individual UDGs. One of the most puzzling aspects of UDGs is their apparent ubiquity across different environments. While initially discovered in galaxy clusters, subsequent studies have found UDGs in a variety of cosmic settings, from the outskirts of clusters to more isolated environments. This widespread distribution challenges simple explanations for their formation and suggests that multiple pathways may lead to the creation of these diffuse giants. The origin and evolution of UDGs remain subjects of intense debate and research. Several formation scenarios have been proposed, each with its own implications for our understanding of galaxy evolution. One hypothesis suggests that UDGs are failed galaxies, where early quenching of star formation prevented them from building up a normal stellar population. Another proposal is that they are the product of extreme feedback events, where powerful supernovae or active galactic nuclei expelled much of the gas from young galaxies, halting star formation and causing them to puff up to their current diffuse state. The role of dark matter in shaping UDGs is a particularly intriguing area of study. Some UDGs appear to be heavily dark matter dominated, with mass-to-light ratios exceeding 100 in solar units. The most extreme example is Dragonfly 44, a UDG in the Coma cluster that appears to have a dark matter halo as massive as the Milky Way's, despite containing only 1% of its stars. This has led some researchers to propose that UDGs could be pure dark matter galaxies, with an unusually low efficiency of converting their gas into stars. However, the dark matter content of UDGs is not uniform across the population. In a surprising twist, some UDGs appear to be deficient in dark matter. The galaxy NGC 1052 DF2, for instance, was found to have little to no dark matter, challenging our understanding of galaxy formation in a dark matter-dominated universe. These apparently contradictory findings highlight the diversity within the UDG population and suggest that multiple formation pathways may be at play. The study of UDGs extends beyond optical observations. Radio observations, particularly of the 21 cm line of neutral hydrogen, have provided crucial insights into the gas content and dynamics of these galaxies. Some UDGs have been found to be surprisingly gas-rich, while others are gas-poor, adding another layer of complexity to their nature. X-ray observations have been used to probe the hot gas content in and around UDGs in cluster environments, providing constraints on their interaction with the intracluster medium. The implications of UDGs for our understanding of galaxy formation and evolution are profound. Their existence challenges models of galaxy formation that predict a tight relationship between galaxy size and stellar mass. The diversity in their properties, from dark matter content to gas fraction, suggests that the pathways to forming these diffuse giants are more varied than initially thought. Understanding UDGs may require a re-evaluation of the processes that regulate star formation and galaxy growth in low-density environments. Recent technological advancements have opened new avenues for UDG research. The development of large, low-noise CCDs and specialized data processing techniques has enabled deeper imaging surveys, potentially revealing even fainter and more diffuse galaxies. Integral field spectroscopy, which provides spatially resolved spectra across galaxies, is beginning to be applied to UDGs, offering insights into their stellar populations and internal dynamics. Looking to the future, several key questions about UDGs remain to be answered. What is the full extent of the UDG population, and how do their properties vary across different environments? How do UDGs evolve over cosmic time, and what is their relationship to other types of low-surface brightness galaxies? Can the apparently contradictory findings regarding their dark matter content be reconciled within a single theoretical framework? Addressing these questions will require continued advancements in observational capabilities and theoretical modeling. Upcoming facilities promise to revolutionize our understanding of UDGs. The Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSST, will provide unprecedented deep, wide-field imaging that could reveal vast numbers of UDGs across the sky. The James Webb Space Telescope, with its exceptional infrared sensitivity, may be able to probe the stellar populations of UDGs in unprecedented detail, potentially revealing their formation histories. In the radio regime, next-generation facilities like the Square Kilometre Array, SKA, will map the neutral hydrogen content of UDGs with extraordinary sensitivity, potentially detecting these systems out to greater distances and in a wider range of environments. In conclusion, ultra-diffuse galaxies represent a frontier in extragalactic astronomy, challenging our understanding of galaxy formation and evolution. From their role as dark matter laboratories to their implications for the efficiency of star formation in the universe, UDGs continue to surprise and intrigue astronomers. As we push the boundaries of observation and theory, these ghostly giants promise to shed light on some of the most fundamental questions in astrophysics and cosmology, potentially revolutionizing our understanding of the universe's structure and evolution. As we contemplate the enigmatic nature of ultra-diffuse galaxies and their implications for our understanding of cosmic structure, we are reminded of the power of observational astronomy to unveil the hidden aspects of our universe. This brings us to another fascinating frontier in astrophysics, the field of galactic archaeology. By studying the chemical compositions and motions of stars within our own Milky Way and nearby galaxies, astronomers are piecing together the history of galactic formation and evolution, much like archaeologists reconstruct ancient civilizations from fragmentary remains. Let us now turn our attention to this cosmic detective work, exploring how the stars themselves tell the story of our galactic past and future. Galactic archaeology, a burgeoning field at the intersection of astrophysics and cosmology, seeks to unravel the complex history of galaxy formation and evolution by studying the chemical compositions, kinematics, and ages of individual stars. This cosmic detective work allows astronomers to piece together the narrative of galactic assembly, much like archaeologists reconstruct ancient civilizations from fragmentary remains. By examining the stellar fossil record preserved in the Milky Way and nearby galaxies, researchers are gaining unprecedented insights into the processes that have shaped our cosmic neighborhood over billions of years. The concept of galactic archaeology emerged in the late 20th century as a natural extension of stellar population studies and chemical evolution models. However, it wasn't until the advent of large-scale spectroscopic surveys and high-precision astrometry that the field truly came into its own. The fundamental principle underlying galactic archaeology is that stars retain chemical signatures of the gas from which they formed, providing a window into the conditions present in galaxies at different epochs of cosmic history. One of the primary tools in the galactic archaeologist's arsenal is high-resolution spectroscopy. By analyzing the absorption lines in stellar spectra, astronomers can determine the abundances of various elements in a star's atmosphere. These chemical fingerprints offer crucial clues about the star's age and origin. For instance, older stars tend to have lower overall metallicity, abundance of elements heavier than helium, and different ratios of certain elements compared to younger stars. The alpha elements, E, G, oxygen, magnesium, silicon, are particularly informative, as their relative abundances can indicate whether a star formed from gas enriched primarily by core collapse supernovae, characteristic of early, rapid star formation, or by a mix of sources including type Ia supernovae, indicative of more prolonged star formation histories. The Sloan Digital Sky Survey, SDSS, has been instrumental in advancing galactic archaeology. Its SEGWAY, Sloan Extension for Galactic Understanding and Exploration, and Apogee, Apache Point Observatory Galactic Evolution Experiment, subsurveys have provided spectroscopic data for hundreds of thousands of stars across the Milky Way, enabling detailed mapping of chemical abundance patterns throughout the galaxy. These surveys have revealed complex structures in chemical space, such as the alpha-enhanced and alpha-poor sequences, which correspond to different components of the Milky Way's disk and halo. Complementing spectroscopic studies, astrometric measurements have revolutionized our understanding of stellar kinematics and galactic structure. The European Space Agency's Gaia mission, launched in 2013, has provided unprecedented precision in measuring the positions, distances, and proper motions of over 1 billion stars in the Milky Way. This wealth of data has allowed astronomers to construct detailed maps of stellar motions, revealing the dynamic structure of our galaxy in exquisite detail. The discovery of phase space substructures, such as stellar streams and moving groups, has provided direct evidence of past accretion events and the hierarchical buildup of the Milky Way. One of the most significant discoveries in galactic archaeology in recent years has been the identification of the Gaia-Enceladus merger event. By combining Gaia data with spectroscopic information, researchers uncovered evidence of a major collision between the proto-Milky Way and a dwarf galaxy about 10 billion years ago. This cosmic crash brought in a substantial amount of stars and dark matter, significantly influencing the structure and evolution of our galaxy. The ability to reconstruct such ancient events demonstrates the power of galactic archaeology in unveiling the dynamic history of galaxies. The study of chemical evolution in galaxies has been greatly advanced by the development of sophisticated models that track the production and distribution of elements over cosmic time. These models incorporate our understanding of stellar nucleosynthesis, supernova yields, and gas dynamics to predict the chemical signatures expected from different galaxy formation scenarios. By comparing these predictions with observed abundance patterns, astronomers can constrain the star formation histories and assembly processes of galaxies. Galactic archaeology extends beyond the Milky Way to nearby galaxies as well. The Andromeda Galaxy, M31, our nearest large galactic neighbor, has been the subject of intensive study. Projects like the Pan-Andromeda Archaeological Survey, PANDAS, have mapped the extended halo of M31, revealing a complex network of stellar streams and satellite galaxies that trace its accretion history. These observations provide a valuable external perspective on galaxy evolution, complementing our inside-out view of the Milky Way. The field of galactic archaeology has also shed light on the nature and distribution of dark matter in galaxies. By studying the kinematics of stars in the outer reaches of galaxies, astronomers can probe the gravitational influence of dark matter halos. The discovery of highly radial stellar streams in the Milky Way's halo, for instance, provides constraints on the shape and extent of our galaxy's dark matter distribution. Recent technological advancements have opened new avenues for galactic archaeology research. Multi-object spectrographs, capable of obtaining spectra for hundreds of stars simultaneously, have dramatically increased the efficiency of large-scale surveys. Adaptive optic systems on large ground-based telescopes allow for high-resolution spectroscopy of individual stars in nearby galaxies, extending the reach of detailed chemical analysis beyond the Milky Way. Looking to the future, several key questions in galactic archaeology remain to be addressed. How did the various components of the Milky Way, the thin disk, thick disk, bulge, and halo, form and evolve over time? What is the full accretion history of our galaxy E, and how typical is it compared to other galaxies of similar mass? How do the chemical evolution histories of different galactic environments relate to their star formation histories and dynamical evolution? Answering these questions will require continued advancements in observational capabilities and theoretical modeling. Upcoming facilities promise to push the boundaries of galactic archaeology even further. The James Webb Space Telescope will provide unprecedented views of resolved stellar populations in nearby galaxies, potentially revealing their formation histories with new clarity. Ground-based, extremely large telescopes, like the 30-meter telescope and the European Extremely Large Telescope, will enable high-resolution spectroscopy of individual stars in more distant galaxies, extending the reach of detailed chemical analysis. In the longer term, proposed space-based interferometers could potentially resolve individual stars in galaxies beyond the local group, opening up new frontiers in extragalactic archaeology. The implications of galactic archaeology extend far beyond the field of astronomy. By reconstructing the history of galaxy formation and evolution, we gain insights into the fundamental processes that have shaped the universe as a whole. This knowledge informs our understanding of cosmology, the nature of dark matter, and the conditions necessary for the development of life in the cosmos. Moreover, the techniques developed for galactic archaeology have applications in other fields, from data mining to pattern recognition in complex datasets. In conclusion, galactic archaeology stands as a testament to the power of modern astrophysical techniques to unveil the hidden history of the cosmos. By reading the chemical and kinematic signatures imprinted in stars, astronomers are piecing together the complex narrative of galactic evolution, from the first generations of stars to the diverse ecosystems of modern galaxies. As we continue to refine our methods and expand our observational reach, galactic archaeology promises to reveal ever more detailed and comprehensive views of our cosmic origins and evolution. As we reflect on the intricate detective work of galactic archaeology, we are reminded of the vast scales and profound questions that astronomy allows us to explore. From the smallest subatomic particles to the largest structures in the universe, our quest for understanding continues to push the boundaries of human knowledge and imagination. This eternal pursuit of cosmic mysteries leads us to contemplate not just our past, but also our future among the stars,